just wonderful. Indonesia is a wonderland.
Kota baru ujungnya berbeda, berbeda bagaimana ku di Salangkara, bagaimana ku di Salangkara. Bertemu lawanlah Adinda, Adinda iman di dadara sama layang, iman di dadara sama layang. Sayang, sayang si patokaan matego, tego gorokan. Sayang, sayang, sayang si patokaan matego, tego gorokan. Sayang, sajojo, sajojo. You madam komi sabab pare samuna muna muna keke, samuna muna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium merah pipinya. Kampunan jauh di Mato, Kunwangsan sebaku liliang, takkan ajo kawan-kawan alamu, sangke basur yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia. Hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara saksama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945.
always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for the unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya bermegah, bermegah, bagaimana di sana sekarang, bagaimana di sana sekarang. Bertemu lawanlah adinda, adinda iman di dada rasa melayang, iman di dada rasa melayang. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampungan jauh di mata, kunwasan seberkuliang, takkan aja kawan-kawan lama, sangke basuh yang suria.
Always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage.
Good morning, everyone. We will shortly start the workshop. And okay, maybe the operator all is ready. Okay, hello, good morning and good afternoon, everyone. Nice to see everyone here in the Zoom meeting. So, welcome to the ICTP workshop on classical and quantum machine learning for condensed matter physics. On the behalf of the organizer, thank you very much for joining this workshop. And I am Eddie from Research Center for Quantum Physics, National Research and Innovation Agency, usually called GRIN, Indonesia. I will be a moderator for this morning session. And it's a great pleasure for us to co-host this event along with the International Center for Theoretical Physics, or ICTP, also with the University of Indonesia and Institute of Technology Bandung. Before we start the workshop, let me remind you some information related to this workshop. This workshop provides an overview of machine learning and quantum computing techniques, in particular to solve condensed matter physics problems. This workshop consists of 3 days, and each day around 5 hours, including 1 hour break. And for this second day of the workshop, we have 1 keynote presentation and 3 contributed talks. We also have a hands-on session in the afternoon session or after the break. Due to limited time in the Zoom meetings, we also provide a Discord server for discussion outside this Zoom meeting. You can also ask questions in the Discord, and please join the server if you haven't joined yet. And then maybe the organizer will share a link again to enter the Discord server. Okay, now we will enter the keynote presentation given by Professor Andrian Bayu Suksmono from Institute Technology of Bandung, Indonesia. And he already joined with us. Good morning or good afternoon, Professor Andrian in Indonesia. How are you?
Yeah, fine, thanks. So, good morning, everybody. So thanks
Morning.
for attending these seminars.
Yeah, thank you very much, Professor, for your availability. But maybe unfortunately, due to his condition problem, he cannot present directly. But we have prepared the video for his presentation, and we will stand by during this Zoom meeting to answer your question. So maybe before we start the presentation, I will briefly introduce his profile first. And Professor Andrian studied for bachelor and master degrees at Institute of Technology Bandung, Indonesia, with 2 different majors, which are physics for bachelor degree and electrical engineering for master degree. And then Professor Andrian obtained his PhD degree from the University of Tokyo, Japan, at the Faculty of Engineering. He is currently a professor at the Department of Electrical Engineering, Institute of Technology Bandung. He is also a senior member of Institute of Electrical and Electronics Engineer, or IEEE. And the main research topic are compressive sampling, imaging, and quantum computing. Now he will present about quantum approximate optimization algorithm. Of course, we certainly cannot wait to hear Professor Andrian presentation and discuss further with him. However, just to remember, after the presentation, we will have around 30 minutes question and answer session. And during or before Q&A session, we allow everyone in the Zoom meeting to write your question in the chat responsibly. And if you want to ask question via video or show your audio or video, please raise your hand first or ask permission via chat, and then we will allow you to unmute yourself. Okay, without further ado, please, I will start the presentation. Please enjoy the presentation.
In this section, we will discuss quantum annealing. So what is annealing? Annealing is a terminology in metallurgy and material science, which means it is a heat treatment, the process that changes the physical and sometimes also chemical properties of a material to increase ductility and to reduce hardness. And the annealing process requires the material above its crystallization temperature for a set of amount of time before cooling. And it is also simply can be summarized that it is a technique involving heating and controlled cooling of a material to alter its physical properties. And this annealing process that inspired the optimization, a particular optimization that it is called the optimization by annealing. And it is an optimization procedure or algorithm that inspired by the annealing process to get the best optimal point solution of a problem. So initially we have classical annealing. It is also called the thermal annealing or the simulated annealing. And SA is a probability technique for approximating the global optimum of a given function. And especially, it is a meta-heuristics to approximate global optimization in a larger space for an optimization problem. So it is achieved by reducing the temperature. So it can be associated with the energy or error function of the cost function. And here we can see here the general formulation of the simulated annealing as pseudocodes. So it is started at a particular state as 0, and then it is reduced, the temperature reduced, and the transition is made probabilistically. Sometimes it is a lot when the global temperature is rise, then with a particular probability it is accepted, or if the new state give lower energy, it is absolutely accepted. And at the end, we will find the final state with the lowest possible energy that can be achieved by this algorithm. And now we will discuss the quantum annealing. We can see here that suppose we have two minima here. The first one is the local minimum. The second one is a global minimum. In quantum annealing, it allows the states to do the quantum tunneling across this energy barrier. In contrast, in thermal annealing, it should be jump this energy barrier. And in general, we can formulate as Hamiltonian, which consists of the kinetic and potential Hamiltonian. And we will reduce one energy, then increase the other one, and later we will know which one that we want to reduce and which one we want to increase. And which in actual case we can do by using quantum annealer, which is produced by the D-wave system. Again, this is the Hamiltonian of the quantum annealing process. We have its kinetic and its potential. Its kinetic will drive the Hamiltonian, so that at the final state we get the solution, whereas its potential encodes the problem of the Hamiltonian. And in this curve we have the kinetic is reduced and the Hamiltonian potential will be increased, and eventually, whereas at the initial state the state of the system reset here, and then it is approximated, the curve is approximated by the final the potential Hamiltonian, so that this point will correspond to the solution of the problem that we want to find. For an example, we will using a problem that I call the finding Hadamard matrices by using quantum annealer.
So what is a Hadamard matrix? By definition, it is an orthogonal binary matrices which interest are -1 and +1, and it has various applications, such as for orthogonal codes in the digital communication system CDMA. It is also used in error correction code with maximal error correction capability, and it was employed in Mariner 9 spacecraft, and it is also used in the experiment design, which is explained in the Hidayat papers. And in terms of its importance in scientific and mathematics, we know that there is a conjecture called the Hadamard matrix conjecture, which is about 100 years old unsolved problem. And why finding Hadamard matrix is hard? We know that since the element of Hadamard matrix is -1 and +1, okay, so they are binary. If we have an M-order matrix, which means that we have M by M matrix, there will be to the exponent of M squared, 2 to the power of M squared, and it is about exponential M squared of binary matrices. And Hadamard matrix conjecture predicts that there is a Hadamard matrix for every M multiple of 4k, where k is specific integer. The problem is how to find it. So if we are using brute force and we consider the worst case condition, then one should check all of the binary matrices, which is a big O exponent M squared problem. So this is actually a hard problem. And in this presentation, we propose to use a quantum computer to help us finding the Hadamard matrix. One of the earliest methods to construct a Hadamard matrix is by using Sylvester method. In this method, we started with 1 by 1 Hadamard matrix, each one, and then we can easily get the H2, which is 2 by 2 Hadamard matrix. Since there are only 4 entries, then we can try every possible 1 and -1, and we can normally have 1, 1, 1, -1 Hadamard matrix. And then from this we can do the Kronecker product or the tensor product of the next level order. For example, it's 4. Then we do the tensor product of H2 by H2, and so forth for the higher order Hadamard matrices. So here, if we have order 2 to the power of k, then the H2 to the power of k can be obtained by tensor product of H2 by H2 to the power of k -1. So the order of Sylvester Hadamard matrices should be 1, 2, 4, 8, 16, etc. to the 2 to the power of k. And this is the limitation of the Sylvester method. It's only capable to construct the order of 2 to the power of n Hadamard matrices. So for example, for Hadamard matrix of order 12, we can use this method. And there are other methods for order 4k. For example, Paley, Baumert, Hall, Williamson. But this method, by using this method, we cannot find all of the 4k order Hadamard matrices. So for the order under 2000, we have several Hadamard potential Hadamard matrices. Actually, this is a binary matrix, but we don't know if they are Hadamard or not. So, for example, the order of 668, 716, 892, etc., up to the 1964. We don't know if these matrices are exist, or how we can describe this matrix, the form of this matrix.
So the main idea of this method is exploiting the orthogonality condition of the Hadamard matrix, which is a Hadamard matrix multiplied by its transpose should be equal to identity. So let's start with a binary matrix P, and in general, B transpose multiplied by D, we will define it as D, an indicator matrix. And in general, D will not be equal to I. Then we flip elements of B, which are Bij, such that D approaching I. And finally, we hope that it will be equal to I. So let D equal Dij, and we define the error energy E as the sum of absolute values of the off-diagonal entries of D, which is E equal sigma absolute value of Dij, and specifically we will take a quadratic value of Dij and then minimize E by flipping Bij. So if we have an entry which value is 1, we flip into -1, but if we have -1, we flip into +1. So we can consider 2 by 2 Hadamard matrix or a binary matrix like this. And in the quantum solution, we will consider this element as spin, and +1 equals spin up, and -1 will be corresponding to spin down. So we can consider this spin configurations, this qubit configuration, which initially has the energy more than 0, so they are not in the ground states in a particular sense. We evolve by the time, so it can be in this form or another forms, and eventually at the final stage they all will be equal. The energy of this configuration will be equal to 0. So for this initial states, which energy in this level, there are two ways to evolve this configuration. The first one is by thermal annealing. We already discussed this case, and in this case we discussed simulated annealing. And in the simulated annealing, this configuration should jump in above this this energy barrier. But if we use quantum annealing, then we can tunneling through this energy barrier. So eventually we hope that they will reside at the ground states, the energy equal to 0, and we can obtain the Hadamard matrix. So this binary matrix then change into this Hadamard matrix. Now let's discuss a little bit detail about the objective or energy function.
First, we have a binary matrix P, which element Big, and Big can be the value of Big is either 0, 1 or -1 plus 1. It depends on which representation we want to use in this case. And for the first case, the initial case, we have -1 plus 1 representation. So we work in a spin variable domain. So this is the binary matrix. We name the element S0, S1, etc. And the next one will be the next column will be SM, SM plus 1, etc. And we have the last element will be SM square minus 1. Then we'll calculate the energy of this binary matrix. And after some simplification, some algebraic manipulation, we get this compact equation. So Ek in the domain of S, we also call it E4 because the highest interaction term is 4-body, will be equal to M squared multiplied by M minus 1 divided by 2 plus 2 multiplied by sigma Si, Sc, Sm, Sn. So this they are all 4-body terms. But we know that quantum annealer like D-wave only takes 2-body interaction terms at maximum. So we have to convert all of these 4 bodies interaction into at the highest will be 2-body. We can take 1 body and 2-body. And we have this formula that we adopted from a paper in a physical review, which say that a 4-body term can be converted into 2-body term by using this expression, this equation. And then we do this automatically by symbolic computing, and we can see here. But after this process, we put back this equation, the energy function, into spin variable equation. So we transform from the initial EKS into the final A2S by using this sequence from EKS to EKQ to A2Q, which is 2-body in Boolean domain, Boolean variable. Then from Boolean variable we convert into a spin variable, and finally we can get the Hamiltonian, the potential Hamiltonian or a problem Hamiltonian H2 hat. Again, because too many terms to do by hand, we need automatic computation. And in this case, we are facilitated with Python. Yes, Python have a package that can do symbolic computing, and we can formulate the computation by using this package. Then, after we have its potential, the problem Hamiltonian, we put it in this equation of quantum annealing. So, in this equation, we have the first is the kinetic Hamiltonian, and the second term is the problem Hamiltonian or potential Hamiltonian. And the potential Hamiltonian can be expressed into this Ising form. Yeah? So we have the first term is Gig, sigma I, sigma G, and the second term will be Hi, sigma I in Z direction. And the driver Hamiltonian or the kinetic Hamiltonian will be can be expressed into minus gamma sigma I hat X. So this is the X Pauli matrix. And we have done various experiments from finding smallest Hadamard matrix. And then we also consider several experiments related to Hadamard matrix. And before going to the detail of the experiment, First, I will explain briefly the D-Wave 2000Q that we use in this research. The D-Wave 2000Q has 2048 qubits, and they are connected by 6016 couplers, and the topology of the connection is chimera graph. The chimera graph, the structure of graph is something like this one, which is a bipartite graph, a bipartite complete graph of order 4, 4. This is the unit cell, and they are connected also by couplers to other groups of the qubits. So what we have to do is this one, D-Wave. We use the D-Wave which is provided by D-Wave Corporation in Canada, and we input our data through a notebook or a personal computer, and they provide a graphical user interface to enter the data. And then by using cloud, we send the data into this computer, and then the annealing, quantum annealing, is run in this computer. In the first experiment, we want to find 2 by 2 Hadamard matrix. Therefore, we have this kind of Hadamard matrix, and S0 up to S3 are matrix elements that we want to find. Then we can calculate the energy of this matrix, of this problem, by multiplication of the matrix with its transpose, and we have this kind of elements in the matrix, but we can simplify. So the D, the indicator matrix, will be like this one. So the first elements, D11, with the simplification of these terms. We know that S0 by multiplied by S0 and plus S2 by S2, S0 will be minus or plus 1. Therefore, their product are square, and it will be 1, and the second one also similarly done, and the value will be also 1. Therefore, 1 plus 1, we got 2. We can do similar analysis to these elements, the 2 by 2. So S1 square plus S3 square will be equal to 2. And the remaining part is the off-diagonal elements, and it contains the variables S0, S1, S2, S3. And because they are asymmetric, we can only consider the upper part of the D, upper diagonal terms of the D. Now we know that the energy is the off-diagonal entries square, so we perform the square of these elements, and we get, after simplification, we get this 1 plus 2, S0, S1, S2, S3 plus 1. Therefore, we can collect the constant into 2 and the remaining variables, like this one. Well, this is the 4 body interaction. So, as explained before, we have to convert to up to 2 terms, 2 body interaction. So after substitution, after transformation that explained before, we can get this A to S display in this part. And as we can see here, we have now we need 5 variables, 5 spin variables. The highest index of this variable is 5, therefore we need 6 variables. And after transformation, we get this equal, so we just replace S with sigma, etc., sigma z from 0 to 5 here. And we can translate this one to the G, which is matrix of containing all of the Ising equation, Ising model. Yeah? So because this is also symmetric, we only display the upper part diagonal of G, and this is the each part, which is 1, 2, 3, 4, 5, 6, 8. So this is the H coefficient, and after we obtaining this G and H matrices and vectors, we can encode it to the D-wave. So we submit by using our terminal to cloud, and it is then sent to the D-wave 2000 Q. Okay, so we continue with this analysis. What happened in the D-wave 2000 Q? This coefficients, this Ising coefficient G and H, will be translated into a coupling strength between the qubits. So we encode this coefficient into this qubits, and because this one we only have a few qubits needed in this coefficient, then we can manually assign the qubits, which qubits that we want to use, and the strength, the coupling strength among the qubits. And after finishing encoding the strength of qubits into the D-wave processor, we can execute the quantum annealing. So we just adopt the default annealing schedule, something like this one. So this is increased, and this one is decreased. The kinetic part of the Hamiltonian is decreased, and the potential problem Hamiltonian will be increased. And after finishing this execution, we get this graph. We get this bar chart showing the distribution of energy against the solution indices. And this one is the occurrence, and we can see clearly here that the lowest energy has a high distribution. So we can forget the other solution, and we just check this one and check whether the matrix or matrices to order Hadamard matrices found or not. And we can see that we successfully found this Hadamard matrix. So by considering plus is equal plus 1 and minus is equal minus 1, we can verify easily that this 2 by 2 matrices in fact are orthogonal. So the next, for order Hadamard matrix needs 4 by 4 or equal to 16 spin variables. But again, we obtain 4 body interaction, and we translate it into 2 body interaction, and then we can get the H2 sigma, or the problem Hamiltonian, which consisting of 389 terms, and the required qubit numbers is equal to 40. And as we can see here, because we have so many terms in the Hamiltonian, we need to do it automatically by using symbolic computing. Okay, then as done like in the 2 by 2 cases, we have to encode the coefficient of this Hamiltonian into the coupling strength between qubits in the D-wave. Automatically, there is a utility in the D-wave that translates the coefficient into the connection between qubits and the strength of connection among them. Okay, so this is the total map of the qubit, and our problem now we have this area. So our problem is mapped into this part of the qubits in the D-wave. Actually, it's about 1/4 or less, a little bit less. So after execution of quantum annealing algorithm, we can have
distribution of the solution, something like this one, similar with before. And after extracting the value of the qubits after observation, then we can find the solution, and actually it is found. So we can verify here that this is the found solution by using quantum computing, which is implemented in the D-wave. Next, we did experiment with finding 3 orthogonal 12-length vectors. So we observed before that the qubit used in the previous problem, only about 1/4 of all qubits are available in the D-wave 2000 and Q. And we want to try higher number of qubits, but if we try to find the next order of Hadamard matrix, which is 4 by 4 and 16, then it is not sufficient. So we try another problem, and in this case, we have 72 variables with 7,765 terms, and after embedding, it needs about 1,766 qubits. So because we have 2048, most of the qubits now occupied or used. Yeah? Most of the qubits are now used, and we can see here in the blue area, almost all of this area are blue. Okay, after execution with a quantum annealing in the D-wave, we can get this distribution of energy and occurrence. And after extracting the value of the qubits after measurement, now we can get there were 1,000 D-wave answer, where 635 was wrong and 365 were correct. And this is the example of the correct answer. And finally, we did the experiment for finding one vector which is deleted from the Hadamard matrix of order 12. So we did one, then we provide 11 of the vectors displayed here. And actually, this is rather a simple problem, and actually it is only required a few number of qubits displayed here. And after some computation, we get H2, the problem Hamiltonian consisting of 38 variables. Sorry, this is 38, 28 H variables, 379 terms, and after embedding, we know that this problem needs 50 qubits. Okay, then again we did the quantum annealing, and there is only 2 solutions we can observe here, and actually both of them are correct. So the solution distribution is something like this. This one is higher than this one, but the number are after summing the probability, they will be equal to 1. And one of the solution is listed here, V11 equal minus plus minus minus 3 plus and minus plus plus minus. And if you put into this set of orthogonal vector, you can verify that actually this one is the solution. Okay, as we see here, we have 2 solutions. This is one solution. So what is the other solution? We found that the other solution is the negation of these vectors. So instead of minus, this one become plus, minus, plus, 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 etc. And it is also a correct solution. Okay, so in this section, we have learned about the concept of quantum annealing, and we consider a study case, which is finding Hadamard matrix problem by using quantum computing, and it is consisting of a formulation of Hamiltonian or energy function, implementation on actual quantum annealer. In this case, is D-wave, and whereas the simplest case is we can only find up to 4 order Hadamard matrix, and we also solving a related QAOA problem, which is finding n set of m order orthogonal vector, finding n missing vector of m order Hadamard matrix. And so this concludes the end of this section. In this section,
We have a second slide. Is quantum approximation algorithm. Maybe the participant who have a question, you can start to type your question in the chat. And let's summarize.
I will explain a kind of a quantum optimization, which is called the QAOA, which stands for Quantum Approximate Optimization Algorithm. So in principle, for a few kind of problem, quantum computers can solve problem faster than the classical computers. This problem includes the short factoring algorithm, the Grover search, and also quantum simulation. But we have to be realistic for present day's condition. And considering the short algorithm, we with error correction, a algorithm require about 1 million qubit and also millions of gates. And regarding the existing quantum device, we are now arriving at this Q, which is a noisy intermediate scale quantum, which means that we only have a few number of qubits. Actually it's hundreds of qubits, but it is still noisy. And such devices cannot handle such problem like the short factoring algorithm for a significant number of digits that we want to factor. And the current quantum computers can be employed to solve only limited specification of a problem. Algorithm that can run on small number of qubits, gates, and shallow circuits can be solved by existing devices. And we want it to be useful enough to solve the real-world problems. It is not demanded, it doesn't need extensive error correction, and it can be implemented on a small number of qubits, which is less than 1000 qubits. So there's a solution proposed here by Ed Farhi, which is called the QAOA, or Quantum Approximate Optimization Algorithm. So why this QAOA is suitable for solving such problem? In the QAOA, we only need low-def circuits. Then it doesn't need too much coherence for the devices. It robust to error, and this QAOA also actually a hybrid classical quantum algorithm. So we can see here that what we mean with the depth of circuit is the length. So the vertical lines indicates the number of qubits, and the horizontal division means the circuit depth. And for the current devices, we only need a few number, as lowest number of depth as possible before the coherence destroyed in the current devices. The general idea of optimization is something like this. So if we plot our configuration space as X, and the energy or relative energy or error of our problem as E, then the objective of optimization is to bring the initial state x0, which initial energy is 0, to the final optimum, the x star and A star. And we see here it is located in the lowest energy state of this problem. So we can say that x0 is the initial phase, and X star is the solution. Here we have a few number of constraints. The first is we have only limited computing resources, space, or in this case, in the quantum computing case, it is qubits, and also the coherence. And we are also limited by the time, so we want to solve this problem as fast as possible and not too long actually. And the best way is to manage, and we want the best way to manage local minimum traps. So we have two options right now that we call it the classical way to manage the local minimum, and also we will discussing the quantum algorithm or quantum way to manage the traps. And basically in the QAOA we have a problem which is then translated, which is represented by Hamiltonian, each consisting of some numbers of sub-Hamiltonian, h1, h2, etc. to hn. And by unitary transform, we want to evolve this h to the solution. And it is represented as u h hat t, which is the exponent of minus ei h hat t divided by the Planck constant h bar. And we also consider here that there is a Trotter-Suzuki theorem that make our life easier, which says that the exponent of a plus b, which is they are operators, can be approximated by exponent of a hat divided by n multiplied by a hat exponent b hat divided by n, and these are exponentiated to n. Well, by using this expression, since it's consisting of some terms, we can expand the u into the products of exponent means I x k t over n, where h is the sum of h1, h2, etc. And we can then do the computation by using this picture that we have u1, uh1, uh2, which is cascaded into a particular circuit. Then we also remember that our objective is to bring the state from this zero state to the optimal solution. So again, we want to evolve our Hamiltonian to the solution. We have here the Hamiltonian consisting of two factors, two terms. I mean, the problem Hamiltonian, which we can denote it by hc, and the mixture of driver Hamiltonian, which here we denote it by hm. So it will consisting of hc and hm with a coefficient gamma and alpha. And by using Trotter-Suzuki composition, we can cascade the circuit into this operation. A minus h1 t over n, then it is cascaded into h2, etc. And we can represent our problem by using a parameterized circuit. So in the parameterized circuit, because we have two terms in the h, the Hamiltonian, then it consists of two blocks, exponent of minus e gamma hc cascaded by exponent minus e alpha hm with coefficient gamma and alpha. Then by considering the Trotter-Suzuki decomposition, we can cascade these parameterized circuits into n numbers of blocks, and ideally the number is as large as possible, but of course it is limited to our resource, our computing resource. And the QA algorithm will working something like this. First, we initialize beta and gamma in the parameterized circuit. So it's represented here in this block diagram. So we prepare the quantum state, psi, ket psi with parameter beta and gamma. Then we compute the expectation we calculate the expectation of H, and now we get the energy level, energy at this stage, and then we input it into a classical optimizer, and we updated the parameters beta and gamma into a new one, and it is then iterated inside this loop until it is convergence. So if we can see here, we repeat under convergence, the criteria be satisfied. So prepare the state psi, cat psi beta gamma using QAOA circuit. The second step is measure the state in the standard basis. Then we calculate the expectation of HP, our problem, and then find the new state parameters by updating the beta and gamma using classical optimization. So this part is classical, this part is quantum, and that's why we call it as a hybrid quantum classical algorithm. And then at the stage 5, we set the current parameters beta gamma equal to the new parameters that we obtain from the classical optimizer. So for illustration, I will give you 2 examples. The first one is widely known max-cut problems, and it is often used as an example for the QAOA or for a more general binary optimization, whether it is using a classical or quantum algorithm. The max-cut problem is something like this. So we have a graph consisting of vertices and edges that connect those vertices, and we want a cut that maximize a particular metric. So a maximum cut is a cut whose size is at least the size of any other cut. That is, it is a partition of the graph vertices into 2 complementary sets S and T. So we divide the vertices into a subset, 2 subset, and we want a graph that connect from one vertices, a set of vertices into the other set of vertices, and such that the number of edges between S and T is as large as possible. That's why it is called max cut. So then let's consider this simple graph, and I take it from a web, Penny Lane web, but actually it works for other quantum programming language. We have 4 vertices, 0, 1, 2, and 3, and we divide into 2 subsets, the vertices into subset A and B. And how to find the max cut? In the proof of method, what we do is we try exhaustively all possible binary assignment, and that's why it is it is a hard problem. It's difficult because we have to try all the binary assignment of the number of vertices. And in quantum computing, what we do is we translate this into Ising model, the first step, and then we solve the problem. And what we seek for is the partition of vertex into 2 sets, A and B here, with the colors, illustrated with 2 colors, which maximize the cost function Cz, where Cc is the sum of C alpha Z. And in this case, Ci we will set it as 0 if it is vertex A in the set A, and we indicate it as 1 if it is in vertex in a subset of vertex B. Then we build the QAOA circuit. We denote the partition using computational basis as cat Z, and we represent the objective function as an operator C alpha, which is equal to half of 1 minus sigma Z J sigma Z K. And QAOA started. We start this process by setting all of the qubits, the input qubits, into uniform superposition. Practically, it is done by inputting all of the qubits into a Hadamard gates, and we can represent the result as cat plus n, which is the sum of Z for all combination of 0 and 1 n-length vector. Then we perform a sequence of operation. So for a state in gamma comma beta. Then we perform UB, UC, UB p minus 1, UC p minus 1, etc. up to UB 1, UC 1, which operates at our to our uniform superposition. Here, UP is the product of exponent minus p beta sigma Cj, and UC is the product of exponent minus e gamma e 1 minus sigma z sigma k over 2 divided by 2. The quantum circuit corresponding to Hamiltonian will be looking something like this. The left hand is the problem Hamiltonian, and it actually exponent of minus I gamma L multiplied by 1 minus sigma z sigma k divided by 2, and it is implemented as 2 qubit with CNOT operation from 1 qubit to the k qubit, and we have here rotation along z-axis by angle gamma L. Then it is also followed by CNOT operation. And in addition to problem Hamiltonian, we have a driver of mixer Hamiltonian, and it is represented by rotation to the x-axis with angle 2 beta L, which operates on g qubit. We can implement this algorithm, which is this circuit displayed previously, into whatever language that you prefer. And this is the example that we implemented it in Qiskit in a Python language. The upper part is when we choose the number of throttle slice equal to 1, p equal to 1. Actually, we have quite exact solution with 0, 1, 0, 1, which is what we expect. Why we have this solution? We can see here, this is exactly the peak of this histogram. So all of possible outcomes, the bit string will be the x-axis, and the y-axis is the frequency of the occurrence. Well, but you can see here that actually the solution, the cost function solution will be equal to 4, but it is changed from time to time, from step to step, 4 to etc. And we can get a more stabilized solution when we increase the number of slices into, for example, here 2. And the effect you can see here in the histogram, all of the non-solution will be suppressed, and you can two dominant curve histogram here, which correspond to the solution. So one of the solution is 0, 1, shift 0, 1, and you can see here at the final step, it correctly estimate the cost function, which is equal to 4. And for the second example, I present how to employ the QAOA to find Hadamard matrices. As before, Hadamard matrix is a binary -1 + 1 matrices, and it has a wide application as orthogonal codes, which is used in CDMA. It's also used as error correction code with maximal error correction capability, which was employed in Mariner 9 to protect the Mars images that are sent to the Earth. And why finding Hadamard matrix is hard? Actually, for a particular order, it is very easy to construct the Hadamard matrix, but for some order, it is very difficult. And if we use a brute force, then we have to check all of the m² number of changing the elements of the matrix from -1 to 1 until we find it is orthogonal, and it therefore needs exponent m² binary matrices, or to be exact, to the power m². We have here a famous conjecture of Hadamard matrix, which predict that there is a Hadamard matrix for every m equal to 1, 2, 4k, and where k is positive number. So the problem is how to find it. Up to now, we don't have a general algorithm to find every or to check at least to every order of n. And so we can use the brute force. But brute force itself is a hard problem because it is exponentially hard. And in this case, we try to use a quantum computer to help us finding the Hadamard matrices. So here I display a few number of Hadamard matrices. The lowest few lowest order. So 1 is also Hadamard matrix, and for 2 by 2 Hadamard matrix we have 1, 1, 1, minus 1, 1, minus 1, 1, 1, and you can check that these matrices are orthogonal. So you just multiply, you just perform the product from one row to the other row, and the pair of rows should be equal. The product should be equal to 0. And for the order 4, we have this something like this, and it is actually very easy to construct by using the Sylvester method. And what we want to do as an example is we want to find all of these two order as a non-trivial case, and by using QAOA, therefore we change the element here with some variables. So we want to check interaction and body interaction in this case. This is one body, S1, S1, S2, S2 body, and etc. up to 4 body interaction. And for this purpose, we have to define a kind of energy function that eventually later we will translate it as a Hamiltonian. The energy function indicates the deviation from the orthogonality condition. It has to be a non-negative value, and we define it as E, which is square sum of the off-diagonal values of a matrix that we call T, where T is the product of transpose of its with itself. So since it is a function as Si, then A is also a function of Si. And finally, later, if we want to implement this algorithm to quantum devices, we have to convert ESE to Hamiltonian.
Sorry, Prof. Andrea, maybe the slide, the content is the same with the previous one, or we can stop here or continue this around 10 minutes again, and we have already entering the question and answer session. How about you, Prof. Andrea?
The slides is different. This
Oh,
is
different.
QAOA.
Okay.
Yeah. So if
Okay.
it is allowed, then please continue the video.
Okay, maybe we continue the video. Thank you.
So for one body term, we have this problem. So we want to know what is the value of S1, and this is very easy actually. You just calculate the energy we get here, 1 plus S1 squared, and by knowing that S1 squared equal to 1, we get 2 multiplied by 1 plus S1, and it has to be 0 to be minimum. So S1 should be equal to minus 1. When we translate this problem into QAOA, we have two components, two Hamiltonian here. The first one is problem Hamiltonian, and the second one is driver Hamiltonian. For the problem Hamiltonian, we have a circuit something like this, which is represented by a rotation along z-axis with an angle 2ci gamma. And for the driver Hamiltonian, we have Rx with argument the angle beta. And it is also can be used to build this circuit, which is consisting of, you can see here, this is the qubit, the first step is a Hadamard gate that make Q into a uniform superposition of state 0 and state 1. And we have rotation. This is the problem Hamiltonian rotation along x-axis for the driver. At the last state we measure. And after running this circuit, we get this distribution of solution. And here we get all of the solution is equal to 1 because we use ideal simulator without noise. We get solution bit 1. Actually, before we have to assume that since in the Hadamard matrix we have element 1 and minus 1, we have to convert it into 0 and 1. And the variable conversion is 0 will be converted to 1 and 1 will be converted to minus 1. So therefore S1, which is equal to logical value 1, will be equal to minus 1. So this is the correct solution. And for the next experiment, we try to change two variables, two elements into two variables, S1 and S2. We change, for example, these two elements. Again, it is also easily can be found, the solution, that the final is, the energy will be equal to multiplied by 1 plus the product of S1 and S2. So to make A equal to 0, S1 multiplied by S2 should be equal to minus 1, which correspond to S1 minus 1, S2 plus 1, or the other way. Then we can formulate the problem and driver Hamiltonian, which is represented here as this synod circuit from qubit 0 to qubit 1. Then we have rotation along the axis by 2 gamma, and then again synod from qubit 0 to 1. And for the driver, for each qubit we rotate by the angle beta. And then we can encode this diagram into Qiskit, and we get this quantum circuit. So we have two qubit circuits. In this first state, we set it to uniform distribution, and we adopt this diagram, and then we make measurement. And after some sampling, we have this solution 0, 1, and 1, 0, which again after converting into the spin variable, we get 0 equal to plus 1 and minus and plus 1 and qubit bit 1 equal to minus 1. So these are correct solutions. We can do similar things to three-body problem. We have three variable and we have three qubit, and the quantum circuit getting more complicated. And also we have rotate each of this qubit along the x-axis. And after getting this quantum circuit, we can do sampling. We simulate it into Qiskit, and we get this distribution. So you can see here these are the correct solution, because we can see here that zero energy achieved when the combination is something like this. And we can get 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 1, 1. So the number of 1 or the number of the number of n should be odd numbers. And you can check that these are the correct solution. And finally, we can replace all the elements with variables to represent 4-body pair, and we get this 4-qubit circuit. Then we implement it into Qiskit, and we can get this distribution. And this equation indicate that the product of S1, S2, S3, S4 should be equal to minus 1. And you can check here that this distribution, histogram distribution of probabilities is correct. Yeah, they are correct, because the number of 0, which indicates the bit 1, is equal to an odd numbers. So after checking that the solution of every combination
of n body term, 1 body, 2 body, 3 body, and 4 body terms in the Hamiltonian are correct, then we can try it to solve a real problem for finding a larger order of Hadamard matrix. So for example, here we want to find a 12th order Hadamard matrix of Williamson, which correspond to Baumert-Hall of order 36. And you can see here the Hamiltonian, the problem Hamiltonian, which is consisting of 1, 2, 3, 4, 5, 6, etc. And actually we need 8 logical qubits. And because the number of them are very large, we have to develop symbolic computation to translate this Hamiltonian into quantum circuit. And I've done that, and we can obtain this kind of quantum circuit. Then again, we run the QAOA, and we can get this kind of distribution. Actually, from the 10 most common solution, we get the most frequent one, which solution for number of qubit 8 is 0, 1, 0, 1, 0, 1, 0, 1, 1, and it's actually indicates a correct solution. And after the conversion of the solution into n by n, a 12 by 12 binary matrix of -1 and +1, we get this kind of matrix for Williamson. And we can check here that after multiplying it by the transpose of itself, then we get a diagonal entries that indicates this is an orthogonal binary matrix. Also, we can convert the solution into the Baumert-Hall 36 by 36, and we get also the correct solution indicated by this diagonal matrix of the product of the matrix by its transpose. So this is the end of this section.
Okay. That's the presentation from. Sorry. That's the presentation from Prof. Andrian. Very interesting and adds to our insight regarding the quantum optimization algorithm, especially the quantum annealing and the quantum approximate optimization algorithm. And we also obtain insight about the example in real quantum computer using D-Wave. Okay, now we are entering the question and answer session. And in the chat box, there already have some question from the audience, and we can see Prof. Andrian have also answered some question. Maybe I will repeat the question, and if Prof. Andrian will explain more, we let me know. The first question from Bonnie Paul. In general, if the problem Hamiltonian is not of the Ising type, for example, if it is an FXZ Hamiltonian or another form, how can it be implemented using quantum annealer? And maybe Prof. Andrian, would you like to answer more the question, please?
Yeah, can you hear my voice?
Yeah. Yes, I can.
Okay, I already answered, but I will repeat here. D-Wave, so the most used quantum annealer kind of a quantum computer is D-Wave. It only accepts the problem in the form of Ising Hamiltonian. So any problem that you want to solve, mainly it should be optimization problem, and you should convert it into Ising Hamiltonian, then it's become easier. You just take the coefficient of the Ising Hamiltonian, then put it into D-Wave, and then we can process it, and you get the solution, hopefully. That's something like that. Okay.
Yeah,
I
thank
hope
you very
that-
much.
yeah.
Yeah, for the answer. We move on to the next question from Sunil Karki. How do you solve the optimization problem by using this quantum annealing? And
Yeah.
yeah,
Okay, so
this.
if it's dependent which quantum computer do you want to use. In what I've tried in my previous research is, if you want to solve it using D-Wave, which is a quantum annealing machine, then we have to convert it into Ising Hamiltonian. And then after we get the coefficient, we put it into the D-Wave and run the annealing. And then finally we get the answer by measuring the qubits. That's if you are using quantum annealer. Your next choice is universal logic gate quantum computer, such as the IBM or the Google quantum computer. In that case, there are so many other problems that you can solve. But because today we talk about optimization, then I will only explain a bit about the optimization. It is also almost similar to the D-Wave case, but this time you have a better choice. In the case of D-Wave, you have to change your problem into, you have to formulate your problem into the Ising Hamiltonian, which at most you are limited to 1 and 2 body interaction. But if you are using logic, IBM quantum computer, which is a universal logic quantum computer, any number of interaction will not need to be factored into 2 body interaction. That's what I explained in the second presentation. So you can use QAOA algorithm. And if you read about this algorithm, essentially it works like quantum annealing, but instead of you have quantum annealer, you have universal quantum logic gate, and to translate from this problem into universal quantum logic gate, you have to maybe you can read the detail in the QA paper of Farhi, and you have to change the interaction between qubit into the Hamiltonian into the interaction between qubit, and we can get a better result. I'm now working on this area. Thank you.
Yeah, thank you very much for the answer. Okay, next question from Edwi Hasdeo. I do not understand where the quantum tunneling appears in the quantum annealing schedule. The annealing schedule seems just to move kinetic energy to potential energy.
Yes, apologize. It is a difficult question for me. I'm mainly just a user. I know how to make one problem, to convert one problem into a quantum problem, a quantum Hamiltonian. Then because this computer can solve this Hamiltonian, then I translate. I can solve my problem. Underlying principle, maybe you can find it the detail in the publication of physical review or something like that. Then I apologize, I cannot explain it more. Thank you.
Yeah, problem. Thank you. Yeah, maybe we can discuss later. If have some more discussion, maybe you have contact him. Okay, move to the next question from the basis Saikia. What is the reason behind different path of thermal annealing and quantum annealing during evolution towards ground state? What is the
Yeah.
reason behind?
Yeah. That's the essence of this presentation. Essentially, the optimization is you have a problem, which when it is formulated as a cost function or energy function, it is in this energy state, and the solution is down there in the ground state. So you have to move this state into the ground state, and along the way you find different kind of hills and also minimum local minimum trap, etc. And why we use many kind of annealing, because we want a better solution. If the problem has a very thin energy barrier and it is very high, then simulated annealing or thermal annealing will have a difficulty, because when you already decrease your temperature at some point, and it is impossible to jump very high. But if you use quantum tunneling, in principle, you can go through this barrier. That's why we will get a better solution. So essentially, we want various kind of optimization, annealing optimization to get a better solution.
Yeah, thank you very much for the nice explanation. Now, from the Discord server, there are some questions. Maybe first one is, does optimization depend on the layout structure? For example, will it work for long-range interaction? If yes, then will you get the same in the quantum hardware?
Back to the presentation, the subject of this discussion, I interpreted it as the number of layer, the total layer in the QAOA. So in principle, if you have more layer, then you will get a better solution. You can get a better result. I don't know about the interaction. Sorry about that. Thank you.
Yeah, no problem. Thank you. Next, from the chat Zoom, there is question from here. Michael Pini. How does the number of two-body interaction term obtained from the four-body interaction scale with the order of the matrix M? It seemed to grow very fast, which could be a problem for scalability to large order Hadamard matrix. Could you please comment on this?
Yes, that's exactly my problem. So although the D-wave now maybe they claim about 5,000 qubits, I cannot use it to solve rather large finding a rather large Hadamard matrix. Why? Because if the number, so let's say the variable M, the order M, you need essentially you need M to the power of 3. So for example, after 4 by 4, you have 8 by 8, but 8 by 8 is not interesting because it's so trivial. You can just Silverster method. So we move to 12 by 12, 12 by 12, then 10, about 10, around 10. So 10 to the power of 3 is 1,000. This is the order. But actually, you need more. You need more than 1,000 to solve this problem. So this is a very difficult problem. But actually, in the next publication, maybe you can find it in the scientific report in Nature by searching my name. The second paper deals with this problem. So I can reduce from big O to the power of 3 to down to big O to the power of 2. And now I'm working on the universal quantum logic gate, and I can reduce more because it is not limited to the number of interaction between the qubits. So I can reduce maybe to the big O to the power of n. So actually, I need a smaller number, and I'm now working on it. It works for low order, but for higher order and using real quantum devices, which we know is very noisy, then I only get noise, noise. So I cannot get the solution at present time. Hopefully, can better solution in the future.
Yeah, hopefully. Yeah, thank you. Yeah, we have still have some question from the Zoom chat from Rauf. I edit this long question. Considering the limitation of existing quantum annealing machine or QAMs to handle higher order term in the Hamiltonian formulation, device using symbolic computing technique to efficiently find an M order Hadamard matrix. Discuss the computational complexities involved in transitioning from M to the power of 2 variables, or M to the power of 3 plus M to the power of 2 minus M divided by 2 variables, and propose strategies to mitigate this challenge using quantum annealing hardware. Compare the effectiveness of a two-body simulated annealing approach with the outcome achieved by actual quantum annealing hardware in solving this problem. And the question is, describe a method using symbolic computing, type of math, to solve this difficult problem more efficiently. Explain how quantum computer, which are currently limited to simpler problems, could be changed or improved to handle the more complex part of this matrix problem.
Okay. So yeah, I'm trying to grab the question. The symbolic computing. I use the symbolic computing to calculate the Hamiltonian of the problem. So this is rather automatic. If you know the problem, in my problem, it is how to the orthogonal a set of orthogonal binary vectors. We have a general formula, and then to generate the Hamiltonian, I just increase the number of the variable. But if you do it by hand, it's very difficult and it's prone to error because it can be thousands of terms. So one Hamiltonian can consisting of thousands of terms. So you have to do symbolic computing to make it automatic. And maybe the second part of the question, to manage the issue of complexity, in my case, it is how to find a larger order of Hadamard matrix. Then we have to change our view. We have to change our paradigm. So in my case, I changed the paradigm from a quantum annealer to a universal gate quantum computer. And that's changed everything. For example, it's reduced the complexity from big O M to the power of 3 to linear to big O to the big O M. So for example, if you want to solve 1000 by 1000, then you don't need 1 billion qubit, you only a few thousand qubits. That's the advantage of universal quantum computer. But at present time, it is miscue devices. You have so many noise, and the coherent time is also short. Practically speaking, we cannot expect a lot from this kind of device at present time. Yeah.
Yeah, thank you for the question and answer. And next, we still have around maybe 5 minutes the question and answer session.
I can answer later. Maybe just send me the question, and
human problem.
Unfortunately, I don't know. I cannot log in into Discord. They did not recognize my number, so I will send it to the committee, and please spread it
Maybe.
into the participant. Okay.
Yeah.
Thank you. Yeah.
Yeah, thank you. The committee will find the solution for you maybe.
Yes.
Next. And we still have time, and maybe shortly answer the question, please. The question, next question from Paula Choi. Thank you, Prof. Andrian, for nice talk. What are the main challenges in implementing quantum annealing for large-scale optimization problems?
Yeah. Large-scale optimization problem. We have to be realistic. At present time, we only have a few hundreds. IBM, I think they already achieved 1,000, but that's the noise is very dominant. The noise is very large. At this time, I myself work in within the theoretical computing, quantum computing, and then sometime I try it into existing quantum device. Okay, if you don't know, IBM provides you with many quantum computer. You just register and then you can do something. You can try something. I think that's the better way to understand how quantum computer can help you solving your problem. Yeah. So of course we expect in the future the manufacturer achieve million or even a billion number of qubits. That's not for right now, maybe 2030 something like that.
Yeah.
Okay.
Thank you. For the next question from Graham van Goffrier, can you comment on the classical simulability of the system from recent Lie algebraic method? In particular, GSIM. My understanding is that essentially all parameterized quantum circuits which do not exhibit barren plateaus have been shown to be, in theory, efficiently classical simulable.
Yes.
Can
okay.
you-
So I have not much knowledge about Lie algebra method, but regarding the barren plateaus, so this is very important issue, and one of the challenge in my research is also because I face barren plateau, and now we have to think more creatively. So, for example, in the QAOA, so after you translate the quantum, the annealing procedure into QAOA, we have many choice. We have so many choice how to find the theta parameter, the angle parameter of this QAOA structure, the QAOA circuit. The default is given by maybe by Python, Cobaila, etc. But I think we can do more creatively, for example, by employing neural network, deep learning to find the angle. So that's maybe we can find something if we try in the classical domain. QA is hybrid quantum and classical. In the quantum domain, maybe we only do a little, we can contribute a little, but in the classical domain, you have so many optimization algorithms that can help you to solve this problem.
Yeah, okay. Thank you for the answer. And next question from Ituen Okun. Please, is the Hamiltonian a standard one, or can we formulate Hamiltonian based on a particular problem?
Essentially, if we are talking about quantum annealing, it only works for quadratic unconstrained binary optimization problem. So as long as you can translate your problem into this domain, then you can solve it by using a quantum computer. So for the node, then the quantum computer does not necessarily solve every problem you have. It's only efficient for particular kind of problem. That's where you have to seek for your solution. Yeah.
Yeah, maybe the next to last question from Virgin atas fact, what is the fundamental difference between quantum computing and quantum annealing?
Quantum annealing is a part of quantum computing. So quantum computing, you can do many kind of quantum computing. Among others is quantum annealing, and you can employ the universal gate quantum computer. Then in that case, it is will be more general. So quantum computing is a set. Quantum annealing is subset of the quantum computing.
Yeah, maybe the last short question and from David Chawan, can quantum annealing be used for temperature dependent and material phase transformation?
I can quantum annealing be used for temperature dependent and
material phase transformation?
I cannot clear the question.
Oh,
I'm sorry.
Maybe
later if I
use. Oh yeah, okay. Yeah, unfortunately, our time is very limited since time is running out. We will maybe immediately end this keynote session. And yeah, we would like to express our thanks to Professor Andrian. Thank you very much, who has taken the time to share his knowledge and experience in the middle of his current busy schedule. And thank you also for all the participants who enthusiastically attend this event. And we now will move to the second session, which is a contributed talk that will be moderated by Mr. Apriyadi. Maybe Mr. Apriyadi already have it in this Zoom meeting. And yeah, next move to the next schedule. Thank you very much. We will give this Zoom meeting to Mr. Apriyadi.
Okay, thank you, Dr. Edis. So hello everyone. Let me introduce myself. My name is Apriyadi Salim Adam from Research Center for Quantum Physics, PRIN. So I will be the moderator in the next two sessions. So let us move to the next talk by Professor Talal Ahmed Kouduri from University of Dhaka. Are you ready?
Hi.
Okay. And also University of Kansas, USA. So he will talk about enhancing quantum utility, simulating large-scale quantum spin chains on superconducting quantum computer. So just to remind you, time for the presentation is about 10 minutes, and will be followed with a discussion about 5 minutes. So you may start now.
Okay. Can you see my screen?
Yes, great. We can see.
Okay.
Can you close the, okay, now, great. Yep.
Okay. All right. Hi, everyone. First, I would like to thank the organizer for giving me the opportunity to present our work here. So today I'm going to talk about enhancing quantum utility simulating large-scale quantum spin chains on superconducting quantum computers. This work has been done in collaboration with Dr. Wu, Shamim, Dr. Kobir, and so significant evolution in landscape of quantum computing leads to of noisy intermediate scale quantum computers. The question is, can we utilize these NISQ computers to study fundamental physics? Of course, there are challenges like error rates affecting computational accuracy, constraint on qubit numbers that limit the study of complex physics, maintaining qubit stability over an extended period of time. But ongoing advancement in error mitigation techniques and algorithms are enhancing the capabilities of these NISQ computers. So the question we try to see is that basically, can the current quantum computer carry out large-scale quantum simulation of quantum many-body system? So to do the quantum simulation, we considered the quantum quench in frustrated spin-half antiferromagnetic spin chain, whose Hamiltonian contains the nearest neighbor interaction and next to nearest neighbor interaction. For the initial state, we considered the nil state, and for the observable, the staggered magnetization, which captures the antiferromagnetic ordering in a quantum state. We considered the two quench protocol. So in the first case, we evolved the nil state using the isotropic Heisenberg or the XXX Hamiltonian, which can be found by setting J2 equal to 0 and delta 1 from the frustrated Hamiltonian. On the other hand, we also use the dimer Hamiltonian to evolve the nil state. This dimer Hamiltonian can be found by setting J2 equal to J1 by 2 and delta equal to 1 in our frustrated Hamiltonian. And find the variation of the expectation value of this staggered magnetization in quantum computer using trotterization. So for the trotterization of the isotropic Heisenberg Hamiltonian, the building block is basically this 2-qubit unitary or the rotation operator, where the theta contains the nearest neighbor interaction, the total simulation time, and number of trotter steps. This is the first order trotterization, and this is the trotter step. Here we see that we arrange the circuit in such a way we have the even layer and the odd layer and so on. For the second order trotterization, we again can have basically the even layer, odd layer, then the odd layer and the even layer and so on. But then we can merge these two even layer, odd layer, and these two even layer to optimize the second order trotterization circuit in this way. So now we go on for the trotterization Hamiltonian. In this case, the single trotter step, the quantum circuit for the single trotter step contains two implementation. This part actually is the implementation of the nearest neighbor interaction, and this part is the implementation of the next nearest neighbor interaction with two different angle determined by the J1 and the J2. Now we have the trotterization to calculate the expectation value of our staggered magnetization with time. But of course, the current quantum computers are prone to error. So we employ the following quantum error mitigation technique to obtain the expectation value. So we use the zero noise extrapolation, Pauli twirling, dynamical decoupling, and the measurement error mitigation. In the case of zero noise extrapolation, we kind of amplify the noise to certain level, and then we extrapolate back into the zero noise limit to get the mitigated expectation value. Pauli twirling is nothing but basically insertion of Pauli gates across the 2-qubit gates, and averaging certain averaging can actually reduce the off-diagonal error coming from these 2-qubit gates. Using dynamical decoupling, we can actually increase the coherence time of the spectator qubits. So now we have the trotterization. We employ the error mitigation to calculate our expectation value. But of course, I mean, it is crucial to cross-check this result obtained from the quantum computer. So we use two classical methods. One is the direct method, which is nothing but the straightforward computation of the state vector evolution given by this formula. This is suitable for like order 20 qubit. We also use MPS-based method, matrix product-based method. Here we use time-dependent variational principle to calculate the time evolution of expectation value in MPS-based method. This MPS-based computation can handle like order 100 qubit. Now for the result, this is the result for the 20 qubit case. Here we see for the isotropic Hamiltonian, the staggered magnetization for simulation time up to 4. We see that the results from the IBM Sherbrooke agrees very well with the direct computation given by the blue line. Similarly, for the periodic boundary condition for the isotropic Hamiltonian, again we see a good agreement between the IBM Sherbrooke results and the direct computation or the exact computation here given by the green line. So on the other hand, for the dimer Hamiltonian for the open boundary condition, we see that both result from the IBM Sherbrooke and IBM Torino, two quantum computer. They agree well with the direct computation, but the Torino result agrees better compared to the Sherbrooke result. Similar case can be seen for the dimer Hamiltonian with the periodic boundary condition. Here also we can see that basically both Sherbrooke and Torino results agree well with the direct computation, but Torino results agrees better compared to the Sherbrooke result. Now we move to the large scale computation, which is actually the 96 and 100 qubit case. This is the case for the 100 qubit open boundary condition for the isotropic Heisenberg Hamiltonian. Here we see that the result from the IBM Brisbane agrees well with the MPS-based computation. Similar cases, 96 qubit periodic boundary condition for the isotropic Hamiltonian. Again, we see that the Sherbrooke result is also very well agreeing with the MPS-based computation. On the other hand, for the 100 qubit open boundary condition for the dimer Hamiltonian, we see that both IBM Brisbane and the Torino agree well with the MPS-based computation, but previously, as we saw, basically for the Torino result agrees better than the Brisbane. Similar thing can be seen for the 96 periodic boundary condition. Also, we see that both the IBM Torino and the Sherbrooke result are close to MPS-based computation, but Torino result is slightly better than the Sherbrooke result. Finally, we also have the circuit depth and the CNOT gate count from our simulation. Here we see that basically the circuit depth basically remains constant in each trotter step for the isotropic Hamiltonian. Here we see that for the 20 and the 100 qubit case, they're basically the same, means that our simulation doesn't depend on basically the initial number of qubit and kind of like signals the scalability of our simulation. Similar case can be seen also for the periodic boundary condition. Here we see that the 20 qubit case and the 96 qubit cases are close. On the other hand, for the dimer case, we see that the 20 qubit case and the 100 qubit case also remain close to each other in each trotter step. And for the periodic boundary condition, also they're kind of like close. But in this case, I mean, when we go to larger and larger trotter step, means larger simulation time, they kind of like start diverging a bit. For the CNOT gate, isotropic Hamiltonian, here we see that for the 20 qubit case, up to like simulation time up to 4, we see that the CNOT gate count remains up to around like 500. On the other hand, for the 100 qubit case, I mean, it remains up to, goes up to like 2,500 CNOT gate. There is like one difference with the isotropic and the dimer case, which here we see we have the simulation time up to 1, but even up to 1, we see for the 100 qubit cases, the CNOT gate count becomes basically 4,000, which is almost double than the case isotropic case. To conclude, by combining optimized factorization algorithm and quantum error mitigation, we carry an accurate large-scale quantum simulation of frustrated spin half antiferromagnetic spin chain in IBM's quantum computer. The circuit depth staying almost the same at each trotter step signals the scalability of quantum simulation of the spin chain. And finally, the accurate measurement of expectation value for these large-scale quantum system using these superconducting quantum computers establishes their utility to probe the dynamics of more complex quantum many-body system. So thank you very much for your attention.
Okay, thank you very much, Professor Chowdhury, for the nice talk. Very interesting. Now we have discussion time. We already have one question in the chat, so I will read for you.
Okay.
On page 8 and 9, what is the time scale? Typically, how long does the simulation take?
Okay. 8 and 9. So how long does the simulation take? The time scale is basically here. The is in the arbitrary scale because we set the J1 to 1 and the H cut to 1. So this is up to arbitrary scale. So but physically for the case for the 196 and 100 qubit case, the physical time to take the to kind of like carry out the computation took around like 15 to 20 minutes. Yeah, 15 to 20 minutes.
Okay, thank you for the answer. Another question, can you please comment on what the main bottleneck might be on expanding your simulation to the higher spin chains? For example, spin 3/2 will be very relevant to the certain quantum links model.
Okay, right. Thank you for this question. Because, well, the bottleneck, I mean, the thing is that spin 3/2 will require basically the, I mean, each side, the degrees of freedom is now not two-dimensional, right? I mean, not C2, but it becomes C4. So with n, I mean, the scaling is basically 4 to the power n. So, what happens is that we have to deal with like a smaller number of like spin site to handle basically spin 3/2. That will be like one thing, because the scalability will be like hampered because of the Hilbert space itself is larger compared to the qubit case. So that will be one.
Okay, thank you. So I hope that will be answer your question, Mr. Graham. So next question is, could you clarify the benefit and potential limitation of using first order versus second order trotterization for simulating the time evolution of the isotropic Heisenberg spin chain on the superconducting quantum computer?
I see.
Specifically, how does the implementation of the second order trotterization maintain the constant circuit depth?
Okay. If I understand correctly, I mean, for the okay, what are the kind of like a sort of like a benefit of first order, second order? In the first order trotterization, I mean, the kind of like the error scales like inversely proportional to the trotter step. If I go to like second order trotterization, that now the error goes not by 1/r but 1/r square. So basically you can have like less error if you go like higher order trotterization. But there is certain kind of trade-off, because going to higher order trotterization means basically increase of my circuit depth for noisy devices like current quantum computer. I mean, if I have larger circuit depth, then this is kind of like a troublesome. In our case, what we did basically, we reduce the kind of like the circuit depth by kind of like a merging these odd layers and even layer so that we have sort of like an optimized second order totalization, which didn't increase like too much circuit depth, and we carried out the simulation itself. But arbitrary case, I mean, but on the other hand, for example, for the dimer case, I mean, we actually use the first order totalization because if we go to the second order totalization, the circuit depth becomes so large. I mean, it just kind of like doesn't give us kind of like a useful result. So this is a trade-off for noisy devices. I mean, whether we want to do like a first order totalization so that higher order totalization has smaller totalization error, but then there is this trade-off of like larger circuit depth. So yeah, I mean, for the dimer case, we use the first order totalization. Yeah.
Okay, thank you for the answer. So I will pick up one question from Discord, maybe the last question in this session. Is it the circuit depth after transplantation? What is your step size for the time of evolution?
Sorry, can you repeat the question?
Is it the circuit depth after the transplantation?
Oh yeah, so, yes, exactly. Yeah, right. Yeah, this is basically the circuit depth after, not just after transpilation, also after sort of like optimization up to level 3. So that is the circuit depth. Yeah.
Okay. So thank you very much, Professor Koundari. So I will stop this session. Thank you so much again for your great contribution in this session and sharing your research. So hopefully we can invite you again in the next occasion.
Thank you so much. Thank you.
Okay,
Bye.
thank you. Yeah. So let us move to the next contributed talk 5. Yeah. So it will be delivered by Dr. Tiago de Souza Farias. Are you here already? Okay.
Yes, I'm here.
So from Federal University of Santa Maria, Brazil, he will talk about the differentiable Monte Carlo for a spin model. So just to remind you again, the time for the presentation is about 10 minutes, then will be followed with discussion about 5 minutes. So you may start now.
Okay, thank you. Are you seeing my screen?
Yes, great. Yeah.
Oh, thank you. All right. Hello, everyone. My name is Thiago. I am a postdoc researcher from the University of São Carlos and to optimize spin models using Monte Carlo. First, I am going to talk briefly about spin models and the Monte Carlo method. The spin models are mathematical models that are composed mainly by 2 elements, the spins and the exchange interaction between the spins. These spin models can be applied in many different fields, such as materials. For example, spin could be the magnetic momentum, and the exchange interaction would be the interaction between the magnetic momentum of spins. Biological cells, the spins could be the cells themselves. In machine learning, the spins could be neurons. And the combinatorial problems, for example, the traveling salesman problem, could be the cities and the path between the cities. Here's an example of the spin model. It's the classical IZ model, which the spin values can have values of -1 and 1. And the simulation shows the simulation of the IZ model in square lattice as you decrease the temperature. So it goes a phase transition between the paramagnetic phase and the ferromagnetic phase. Now the Monte Carlo simulation. Briefly, there are many methods to simulate spin models. Here you use the Metropolis Hastings algorithm. Briefly, it consists of these following steps. You select a random spin, then you flip its value. You calculate the energy difference between before flipping the value, after flipping the spin value. Then you use this energy difference for accepting the flip if the energy difference is less than 0, else with a probability that depends on the energy and the temperature of the system. So by using this algorithm, you can simulate the spin models just as in the animation I showed before. However, here in these last two steps, the accepting the flip or changing the spin with a probability, these steps are not differentiable, meaning that you cannot take the derivatives of these values with respect to the spin values or the exchange parameters. Thus, we propose an adaptation of the Monte Carlo method to make it differentiable. So the first steps are the same as the Metropolis algorithm. You select a random spin, you change its value, you calculate the energy difference, and you calculate the probability of flipping the spin. However, we adapted these functions to make it differentiable. So you calculate a weight with the logistic function that depends on the probability and a random value. And then you change the spin value according to this weight. So it's the weight times the new value of the spin plus the 1 minus the weight multiplied by the old spin value. Note here that we have a parameter called alpha, and if you take the limit of alpha towards infinity, then this algorithm becomes just the same standard Monte Carlo method. Then after you change the spin value, you can either optimize your system by changing the spin values, or you can optimize the system by changing the exchange parameters. And after that, you can discretize your spin values, because here this method introduces an artifact that the spin values can have more than values between, they can have values between -1 and +1. So it discretizes it for the Ising model to have exactly values of -1 and +1. I'm going to show this method applied to two different problems. The first one is to find the state of lowest energy in the system for the Ising model. So you have a loss function. Here's the loss function is the energy of the Ising model itself. Then you use the differentiable Monte Carlo method to update the spin values. The spin values are updated by doing a gradient descent. So they are updated by taking the gradient of the loss function with respect to the spin values and updating the spin values by gradient descent. Here's eta is a hyperparameter that's similar to the learning rate in machine learning. So for the ferromagnetic Ising model with J, the exchange parameter J equals to -1 for all spins, we compare to the standard Monte Carlo method, optimization only, and the differentiable Monte Carlo method. As you can see here, the differentiable Monte Carlo method can find the state of lowest energy faster than the Monte Carlo simulation only. For the spin glass, the J values are random values that between -1 and +1. And the differential Monte Carlo method can find a state of lower energy compared to Monte Carlo only and the optimization only. Another problem that we apply this method is for the state preparation. You have you optimize your exchange parameter values so that the distribution of spins can have a specific distribution. So your loss function is the square difference between your target distribution spins and the distribution spins that you have. So you optimize the exchange parameter by doing gradient descent on this parameter, taking the derivative of the loss function with respect to J. So here is a animation show the training of this model is the target distribution. So you want the spins to have this specific format, and model, the distribution spins in the Monte Carlo simulation goes towards the target value. So here the parameter exchange, and it goes to the target value. After training, you can do sampling by using standard Monte Carlo method. And after training, as you can see, the Monte Carlo is updating the spin values. And because it optimizes the exchange values, the distribution spins is the same as the target as we wanted. For conclusions, we present a differential Monte Carlo method that allows optimizing spin models by either changing the spin values or the exchange parameters, and you apply it to two different problems. One is the finding the state of lowest energy, and the second is to optimizing the exchange parameters in order to have a specific distribution of spins. For feature scope, there are many open problems that we can apply this differential Monte Carlo method. For example, in combinatorial problems, you can map these problems into spin problems, such as the vehicle halting or the traveling Selesmon problem. Then you could, on theory, apply this method to optimize the routes. And for machine learning, you could apply to Boltzmann machines, for example, for optimizing the neurons. And also we want to extend it to quantum spin models, such as the Heisenberg model. And also you could use this model to investigate material properties, such as topological materials. This is a QR code that goes to the paper related to this problem. I would like to thank the organizer for accepting my talk, and thank you for your attention.
Okay, thank you very much, Dr. Rias. Very nice talk. Now we have discussion time. We already have some question in the chat Zoom, so I will read from Reinhardt. How do you select the random spin? Do you use a random function?
Yes, it's a random uniform distribution. So we use this uniform distribution to sample different values of J and connect the spins between them with these values.
Okay, thank you for the answer. So from Dr. Roni, can the Ising model be formulated on the complex network? How can the interaction energy be formulated considering the non-uniform degree of node in a complex network?
Yeah, here I showed you the Ising model on squarelets. So it's a square network, but you could apply to any different kinds of network. You could apply to graphs, to triangular lattices, and so on. And the second question is how the action energy from considered. So, for example, here I use the Ising model, but you could also apply to different models, such as the Potts model, the Heisenberg model. So you can have different energy formulations and still apply the differential Monte Carlo simulation to optimize these models.
Okay, thank you for the short explanation. So next question from does this differential Monte Carlo work for a continuous spin system like Heisenberg model? Maybe you already mentioned.
Yes, it does. In the Ising model, the problem is that the spin values are discrete. So after you optimize, you have to discretize the spin values because the optimization is continuous, right? So when you optimize the spins, you decrease step by step. So then after optimization, it discretizes to have the spin values. But for the Heisenberg model, we have continuous values. So you don't need to discretize. You can apply the method without this step.
Okay, thank you. So another question from Dr. Eddie. So he mentioned your animation is very funny. Can you extend the work to the SYK model? Sakef Yi-Kitaev.
Yeah, the differentiable Monte Carlo method is a general method that could, in theory, apply to any kinds of spin models. So yes, you could use this model to optimize your parameters of these models, and no problem.
Okay. So another question: how does your method compare to cluster algorithm like Wolf's algorithm? These are typically much faster than flipping a spin in a time.
Yeah, I agree with you that the Wolf's algorithm is faster at flipping time. However, here we use the checkerboard algorithm with the Monte Carlo method that can flip spins in parallel. So every spin that are not connected directly to each other, you can update at the same time. So you can speed up the Metropolis algorithm to have a much faster simulation time by using updating spins in parallel.
Okay. Okay, another question from Julian. Could you share the publication link of this if it is available?
Yes, sure. I will share in the Discord.
Yeah, maybe. Yeah, if you can enter in the Discord server, you may share it the link.
Yep.
Another question from Rukshon Abadi. He just curious about the computational time and computational power. Does it model using less power or time than normal Monte Carlo model?
Is a bit slower than Monte Carlo method because you have an additional step that is the optimization step. So besides doing the Monte Carlo simulation, you have to optimize the system. So it's a bit it's not fast as the standard Monte Carlo method, but it's not very much slow. It's just a optimization layer that you have on top of. So the constraints is the memory. So as long as your spin model fits in the memory, you are good to simulate it.
Okay. Another question. Can we apply differentiable Monte Carlo to quantum computing?
Well, we can adapt the differentiable Monte Carlo method to quantum systems. However, we cannot optimize do the optimization in the quantum computer. The optimization, you can simulate your spin model in the quantum computer, but the optimization you only can do in the classical computer. So you can have a hybrid algorithm where you simulate the spins in the quantum computer and then optimize it using classical computers.
Okay, maybe I will pick one last question in this session. Do you use GPU-based computer in your simulation?
Yes, every simulation I showed here in the presentation, I use the GPUs to speed up the simulation. Yeah.
I see. Okay, great. So due to the time limitation, so I will stop this session, Dr. Farias. If for those who want continue the discussion with Dr. Farias, you may use Zoom chat, also Discord channel, and Contributive 5. So if you can enter in the Discord server. So thank you very much, Dr. Farias, for your great contribution and sharing your research.
Thank you, everyone. Bye-bye.
Yeah, thank you. So next we will have a break time just to give some advice for all participants. Please keep online in this Zoom meeting during break time, not log out or leave the Zoom, because yesterday there were some problem for people who cannot re-enter again in the Zoom unless it is internet problem from their side. So see you again in 1 p.m. In Central European times with other moderator. See you. Thank you so much.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru ujungnya berbeda, berbeda bagaimana di Samangkara, bagaimana di Samangkara. Bertemu lawanlah Adinda, Adinda iman bidadara, Samalayang iman bidadara, Samalayang. Sayang sayang si patokaan makai go gorokan sayang. Sayang sayang si patokaan makai go gorokan sayang. Sajojo you madam komi sa papare sa muna keke, sa muna keke. Soleram, anak yang manis, janganlah dicium, sayang kalau dicium merah pipinya. Kampuangan jauh di Mato, Kunwangsan sebaku liliang, takkan aja kawan-kawan nalamu, sangke basuh yang suria.
Indonesia dengan ini menyatakan kemerdekaan Indonesia hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya berbeda, jauh bagaimana ku di Samangkara, bagaimana ku di Samangkara. Batamu lawanlah adinda, adinda iman di dadara, samalayang iman di dadara, samalayang. Sayang sayang sifat tokaan makai go gorokan sayang 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 sifat tokaan makai go gorokan sayang sajojo you madam ko bisa berpari samuna muna keke samuna muna keke soleram anak yang manis janganlah dicium sayang kalau dicium merah pipinya kampungan jauh di Mato kunwangsan saya berkuliah takkan aja kawan nalamu sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia. hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya berbeda, bagaimana di Salangkara, bagaimana di Salangkara. Batamu lawanlah Adinda, Adinda iman bidadara, Samalayang iman bidadara, Samalayang. Sayang sayang sifat tokaan, makai go tego gorokan. Sayang 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 sifat tokaan, makai go tego gorokan. Sayang sajojo sajojo, yumadam komi sabapare samuna muna muna keke, samuna muna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampungan jauh di Mato, Kunwangsan sebaku liliang, takkan aja kawan-kawan nalamu, sangke basuh yang surya.
dengan ini menyatakan kemerdekaan Indonesia pendataan, dan lain-lain diselenggarakan dengan cara saksama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya Bamega Bamanaku di Samangkara Bamanaku di Samangkara Batamu lawanlah Adinda Adinda iman bidadara Samalaya iman bidadara Samalaya sayang sifat tokaan matego gorokan sayang sifat tokaan matego gorokan sayang sajojo yumanam komi sabapare samuna keke samuna keke soleram anak yang manis janganlah dicium sayang kalau dicium merah pipinya kampunan jauh di mata kunwangsan sebaku lilian takkan aja kawan lamo sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science. Humans have always been curious. Why is the world the way it is? How does the world work?
Photonic states are states of light that have topological properties. These topological states are protected by topology, and they are immune to certain type of perturbation. For example, here we have topological photonic. We have here photonic states for electromagnetic wave that is protected from scattering at this scatterer. So this type of topological states are immune to perturbation and are protected by topology. So the topological aspects of this material is included in what is called topological invariant. Topological invariant, for example, here we have a topological invariant for sphere. So even if we change it, topological invariant is still 0, which here is indicated here as G. But it is different for other type of shape, like torus one here, which have a topological invariant of 1. So different shapes are characterized by different topological numbers. In the context of 1D topological photonic, like this one here, the topological invariant is called Zag phase. Zag phase is defined as the integral here. So in symmetric unit cell, as indicated here, Zag phase takes only 2 values, 0 or 1. And each band, as shown here in this band structure, is either have Zag phase of P or Zag phase of 0, as indicated here for each band. So in the this topological invariant here is defined for infinite crystal. In the finite crystal, or for example, here we have 2 photonic crystals connected at this point, which is called interface. There is what is called a bulk boundary correspondence. You can form the bulk, which is Zag phase, deduce the value of the surface, which is related to topological state at the surface or the interface of photonic crystal. Here we have the relation between the sign of the reflection, which is of finite crystal, to the value of the Zag phase, which is the value of the bar. So this can be simplified here. To give a concrete example, we have here sign of the phase of the first photonic crystal, like one here, and sign of the phase of the second photonic crystal, and combining these two, we can deduce that from the different sign of this photonic crystal that we have a topological state indicated here by zero reflection of the system. And usually in the literature, it's called null state. So now I will talk about the use of machine learning in such photonic crystals. Machine learning is used in two paths or two different methodology for forward design, which, as we see here, we began from geometrical parameters of crystal, and we deduce optical responses like polarization, wavelength, and other parameters. The other strategy is the inverse design. In the inverse design, you start from the optical responses that you want, like example, defined polarization or other properties, and you deduce the geometrical parameters that will give such optical response. In deep learning is used in topological photonics in the same manner. In the forward path, you start by the geometric parameters for your Hamiltonian, and from that you deduce topological properties like third numbers, Euclidean numbers, and etc. In our case, it will be exactly. In the inverse path, you start by Zag phase or topological property that you want, and from that you deduce geometrical parameters that will give you such properties, which is really important for the design of new and novel topological photonic crystals. So in our case, how we prepare the data for the training of the model. First, we started by a given photonic crystal with defined geometrical parameters. From this photonic crystal, we deduce its band structure, and from its band structure, we deduce the sign of the reflection phase in each gap, as we see here, where red indicate sign of the phase negative of the gap, and the blue indicate sign of the positive sign of the phase of the gap. So from that, we transform it to a vector of defined size that we want for training of the model. And from that, and with repeating for number of samples that we want, you will see this vector of sign of space and geometrical parameters in data files for training of the model. So first, we faced that we discovered that this inverse network it has problem which called unicity problem. That meaning for the inverse there is no unicity. Different for one optical response there is different geometrical parameters that correspond to this system. People in literature have suggested many strategies to overcome this situation. For example, here they suggested to use pre-trained network as the output of the inverse model to train tandem network or the inverse model to give appropriate optical responses or geometrical parameters. So our network is composed as follows: for to have forward network with this defined structure, and these are the parameters of the network. We use it network with these parameters and the CGD optimizers and other parameters. And for the inverse network, we worked with the same strategy. So for the training of the forward model, which is important for the inverse design, we have used different parameters. And as you see here, the forward model is predicting, is in agreement with the real phase. Also, for the unbiased network, as we see here, it is convergent and it is capable of predicting the geometrical parameters of our photonic crystals. So, for validation, we have compared this result with experimental result, as we have here. We have two photonic crystals with two different geometrical parameters predicted by the unbiased design deep learning network. And as we see here, we have different sign of the reflection phase as indicated here by both theoretical and experimental results. And also we have here sign of the reflection phase in each gap. From this, we use the bulk boundary correspondence to deduce the values of the Z phase in each band. And from that, we can engineer topological antiphase set as we want. To conclude, we have studied topological property of one-dimensional photonic system using Z phase, and from that we achieved this by sign of the reflection phase of each band gap. Based on that, we have able to develop a deep learning model for the unbiased design of such structure. For the perspective, we have to work on more complicated materials, such as 2D materials, which are important for application in topological materials. So thank you for your attention.
Okay, thank you, Dr. Eloni, for the nice talk. We'll now open for questions. Any question for Dr. Eloni? Okay, I have a question. If the network we use in is not a complete graph, such as in your presentation, for instance, using a scale-free network, will the machine learning results better than those from complete graph?
Can you repeat the question? I don't understand well.
Yeah, in your presentation, you are using a complete graph for a neural network layer. The question is, if we use not a complete graph, for instance, using a scale-free network, will the machine learning results be better than those from complete graph?
Like if we use different methodologies, are we getting better results? I think there is still more space for optimizing such a structure, but the main idea of this is to suggest that we can unbiased design topological property of such systems. So this work is just to give that the idea that there is such methodology for predicting or designing such a topological state. I hope this answers your question.
Okay, thank you. I see there are several questions in the chat box. I will read. Okay, from Mona. Thank you for your presentation. My question is about the number of neurons in each hidden layer, and how can you justify the choice of MSE and not RMSE or MEA?
So thank you for the question. Actually, in this work, I didn't have use optimization strategies for the neural network. So just I relied on intuition and trial and error. So as I explained, the objective of the work is just to give an example of this strategy so that can be developed further. So the choice of hyperparameter of model was just based on trial and error. I hope this answers your question.
Okay, the next questions from Itwin Okon. Please kindly give a clear distinction between churn and winding number.
So topological states are discovered in early 90s. So first, they discovered that topological materials arise for what is called the use of a perpendicular magnetic field. So people try to explain this. So they found that this topological matter can be explained by topology, and this topology is the churn number. So in this context, they called them churn oscillators. Later on, they discovered that you didn't need the magnetic field. So they discovered another material based on, for example, time reverse symmetry, and these materials are called topological oscillator. So they start to distinguish this material with different topological numbers. So this both winding number and churn number are different topological invariants that are used to describe different topological materials. Thank you.
Okay, the next questions from Gustavo Mangol. Have you seen the recent work with physical photonic neural network? Do you have any insight and on how the topology would affect the design?
Thank you for the question. So, as you indicated, photonic crystals or photonic in general are used for nomorphic computations. So they are trying to emulate the brain of humans using photonic circuits. So this is an important part in science. I think topology, what adds to these materials is it's important for the robustness of such states. For example, recently there is a great interest in topological quantum computer because topology is robust and protect the state from the perturbation. So it is used to enhance the coherence of quantum states. So I think topology is important for the robustness and protection against perturbation in such system, and will play an important role in quantum computation and the photonic systems, devices.
Okay, next question from Edwin Hasdeo. What is a typical material for photonic crystals? Can you give a simple example, the condition to get side of Sachs quasi inverted?
So the materials that are used in photonic crystals are periodic dielectrics with different epsilon, as we studied in the electromagnetic course. So you use different materials with different dielectric properties to engineer photonic crystals at different scales, from nano to centimeter or to macro systems. So these are strategy to design general photonic materials. Sachs phase is, as I said, is geometrical phase, which is called topological invariant. So to get, as I indicated in the slides, that the topological phase is or the surface is a property of the infinite system, which is called the bulk system. Sign of the phase of the reflection is the property of the finite system or the surface system, which have limitation. So the bulk boundary correspondence relates to the surface and the surface. And from that, you can deduce the surface from the sign of the reflection of the phase. And you can use strategies of inverse design, which is already used in inverse engineering to start from surface and deduce geometrical parameter.
Okay, the last question on the chat box from Mir Fahid Husseini. That invariant usually is appropriate for 1D systems. In the network, how one can determine the dimensionality of the system?
Yeah. So as you said, the surface is property of 1D system. So dimension in the network is already defined in the method that you give data inputs. So the neural network doesn't know structure of your system because I am not using, for example, conventional neural network which works on images, but I'm using sample connected neural network. So I give dimension of the system as geometrical parameters, like indicated in my presentation by D1 and D.
Okay, thank you, Dr. Eloni, for the nice talks.
Thank you.
Since our time is up, we will move to the next contributor talks. Once again, thank you for your contribution.
Thank you.
Okay, our next contributor talk will be presented by Dr. Anton Vilanovic from Ural Federal University and Mikhail Institute of Metal Physics, Russia. The title of his presentation is Machine Learning for Machine Learning Prediction of Thermal and Elastic Properties of Double Half Heusler alloys. Dr. Anton, time is yours. Thank you.
Hello, everyone. Can you see my presentation?
Sure.
First of all, Heusler alloys is a well-known system with different interesting properties available for different practical applications. But the idea of double half-life Heusler alloys was initially suggested by Anand in the paper in Joule. So this essentially compounds with a chemical formula of one of these three chemical formulas where X and Y are metals and Z is a P element. And why these alloys are of interest? It is because they possess low lattice thermal conductivity. So for example, from this figure, you can see that indeed conventional ternary Heusler alloys has higher thermal conductivity than the double half Heusler alloys, and this also can be seen from these figures. But on the other hand, so why is this is important? Because if we recall the formula for the figure of merit for thermoelectric materials, we know that it is inversely proportional to the thermal conductivity, so we need to make it lower so to obtain the good thermoelectric material. But on the other hand, because of four different possible elements in the half Heusler alloys, they form a large space of possible compositions, and it's not feasible to study them either experimentally or by DFT calculations because of many possible compositions, and there where the machine learning can help us. So the problem statement of this work was on the basis of DFT calculations data from the open AFLOW-LIP database, construct regression models that allow to predict thermal conductivity and some other properties of a compound, and to apply these constructed models to double half Heusler alloys in order to discover compositions that are most promising for practical application. So we have our data set was made by making the automated queries to the AFLOW-LIP database, and it contained about 5,400 records containing properties of ternary and binary compounds. So you can see from this figure that almost all elements of the periodic system are included in this data set. And if we look at the crystal structures of the compounds, we see that most of them are cubic, but they're also equally orthorhombic, hexagonal, and tetragonal compounds. So then we, by using the MATMiner code, we made two types of descriptors. The first one contains different statistical quantities like mean, maximum minimum values, or mean deviation for elemental characteristics such as element position in the periodic table, covalent radii, electronegativity, and so on, and basic crystal structure features, which are volume per atom or number of space symmetry group. This is a descriptor number 1, which contain 140 features. But in addition, we have made another descriptor number 2, which in addition to these features contain so-called advanced crystal structure features, which are distances between nearest neighbors, length of bonds, and so on. We used, to solve the regression problems, we used gradient boosting algorithm. The choice of this algorithm is motivated by the fact that our studies had shown that it gives the most good accuracy. And let me remind you that what this method is. It is an ensemble method which uses consequently connected decision trees. And what we actually learn in this method is we learn the error produced by the consequently connected decision trees. So, of course, we performed the optimization of hyperparameters of our model by using the randomized search CV procedure with a 5-fold cross validation. The data set was divided into 2 parts. 75% of the records were used for training and the remaining 25% for validation. And now let's look at the results. Here you can see the accuracy. So in the columns, you can see 3 different metrics. R squared is a coefficient of determination, root mean square error, and mean absolute percentage error. So, for example, and in the lines, you can see 5 target quantities, 5 properties. Of course, it is thermal conductivity, but in addition, it's gamma, it's Grunizing parameter, the bi-temperature, B and G are the bulk and shear modulus, and sigma is a Poisson coefficient. So, as you know, the best possible value for the R squared is unity. So, for example, especially for the bi-temperature and elastic moduli, we see that we obtained really close values to unity. A little worse for kappa, but still good enough. And what is also interesting from this table is that you see here columns A and B and what they mean. The A column is a description by without accounting for the advanced crystal structure features, and B is with these advanced crystal structure features. And you can see that there is actually no big difference between them. So in this particular regression problems, this advanced crystal structure features didn't produce any sufficient improvement. But in general, this result give us some rationale that the built regression models they enable to predict properties, and therefore what we did next, we made a descriptor for 180 double half Heusler alloys with established thermodynamic stability. This stability was established in the aforementioned paper by Anand. So we made the descriptors by using the crystal structure data from the open quantum materials database, as well as from published articles. You can see in this figure 3 possible crystal structures for this half Heusler alloys. And in this table, there is a selection of results for some of this double half Heusler alloys. And for example, the first column gives us the predicted, which is ML, machine learning, the predicted values of the thermal conductivity, while in the second column there is a DFT or experimental reference data. And what is most interesting, if you look at the experimental data, which is indicated in red, for example, for this most well-known compound, you see that experimental data is actually closer to the result of machine learning prediction and not to the result of DFT calculations. The same thing can be seen from this row for this compound. Again, we see that DFT calculation for some reason is much higher both than the experimental data and the result of our prediction. In general, from this result, again, we see that our models can be used for prediction for the double half Heusler alloys. And this enabled us to predict the compositions among these 118 compounds with the lowest thermal conductivity. And so here you can see these compositions, the predicted kappa. And it's indeed very low, about 2 watt by meter Kelvin. And what is interesting that all 5 compounds contain magnesium or platinum, palladium, and all these Heuslers of this type with I42D space group. So to conclude, we have built regression models for prediction of properties, and we have applied this model to predict properties of double half Heusler alloys, and the predicted values are even closer to the experimental values as compared to the corresponding DFT data. And in the future, it is planned to expand the list of compositions or build regression models to predict electronic thermoelectric properties such as Zibig coefficient and other important properties. And finally, if you are interested in this research, you can have a look at our paper published in Materials, Chemistry, and Physics. And this QR code will give you the direct link. Thank you for your attention.
Okay, thank you very much for the nice talk. We have several questions, maybe, from Edwi Steel. The first question, Dr. Anton, what is the gamma in the x-axis slide 3, in slide 3?
Mm-hmm. Let's go to
what
this.
What is gamma in the x-axis in slide 3?
Yeah, sure. Thank you for the question. This is actually the Grüneisen parameter. So they have plotted thermal conductivity as a function of Grüneisen parameter to show that there is a dependence between these two quantities, but not so trivial as you can see from this figure.
Okay, next questions. Also from Edwi. What is the axis in slide H2?
Yeah, this is also maybe I did not mention because of lack of time. So these three pictures show us the performance of the models of the training and validation sets. So in the y-axis, we have the result of predictions of by our regression models, and in the x-axis, we have this is a flow leap. This is DFT calculations which were treated as true values. So we trained our models on this flow leap DFT calculation data, and so you can see here that for different properties the correspondence is different. And of course, for the train set, it is a bit better, which are the blue points than the test set. But this is actually usual for the machine learning.
Okay, next questions from Will. Can machine learning be used to predict electronic properties of 2D materials? If yes, how?
Well, I don't see any things that I think, yeah, it's possible. Even I saw some papers regarding such calculations. For example, maybe you have heard about the Jarvis project. They have definitely did something for the 2D materials. I can give you some links in the Discord channel if you want. And I think it was something about maybe like density of states or at the Fermi level, something like this. So in general, yes, I don't see any principal problems for the 2D materials.
Okay, next questions from the data. For hyperparameter optimization, what is the suggested specification of computational power?
Yeah, it's not really a big demand on the computational resources. So these models did not require any computer clusters. So I ran it on my own computer, and it has taken about maybe 3 or 4 hours to optimize the hyperparameters on the 8-core processor. So this is not a very big consumption, because of gradient boosting is actually not very demanding method, or at least for our not too big data set consisting of about 5,000 records.
Okay, the next question from Nura Ibrahim, Dr. Anton. What is the reason for using 25% of the data for validation, and how do you determine the trained data is accurate or good enough?
Okay, concerning the first part of the question, it's I think in general it's a bit arbitrary. So we use this 25% by looking at the experience of other works. However, we have performed some tests for another percent of the data taken for the training and testing, but didn't give us principally different result. And concerning the second part, how do you determine if the trained data is accurate or good enough? Well, I'm not sure how we can determine this in general, but at least I can again point to this table, which you can see that I think if we obtain a good accuracy metrics for this actually big data set with different elements included, I think we can believe that this data is accurate enough for these regression problems.
Well, next question from Edwi. Thank you for your presentation. I might have missed the detail. I guess that you obtain kappa from Condensed, debit temperature, BG, and sigma.
Yes, quite right. So in this table, this quantities is just as you list them. This is a kappa, the phonon part or the lattice part, of course, of this kappa, and then a Grüneisen parameter, Debye temperature, bulk modulus, shear modulus, and Poisson coefficient. Yes.
Next question from Mona Spy. How the crystallographic symmetry can influence the accuracy of each model that you have applied? For the R2, have you calculated from the cross-validation scaffold?
Yes, concerning the cross-validation, when we evaluated this metrics, we have repeated this split of the train and validation set 5 times with different random seeds in order to average the metrics. So this is something like k-fold. And concerning the crystallographic symmetry, yes, we have made such an analysis which has shown that actually there is no principal difference between this different crystallographic systems. So if from DFT, as you know, that it is more problematic to calculate something for the low symmetry compounds than for high symmetry. And in machine learning, we don't face such a problem, and the accuracy doesn't change considerably.
Okay, thank you very much for a nice talk. Because we have limitation of time, the question can be answered via Discord.
Thank you.
Yeah, thank you very much. Yeah, thank you, Dr. Acton, for nice talk. We will now for discussion. We'll move to the next section. Once again, thank you. We have see you again in the next event. Thank you. Okay, our next session is hands-on session by Mr. Yusrul Hana.
Okay.
I believe. Yeah. Okay. Thank you. The time is yours.
Okay. Thank you, Dr. Ronnie. So good afternoon, folks. Okay. Welcome to the hands-on session on day 1. So this is the last session in this today. I am Muhammad Yusrul Hana from Research Center from Quantum Physics, National Research and Innovation Agency. Today, I would like to give a hand-on session about quantum computing with the newest Qiskit package. So for information that Qiskit version, the newest version have different setup compared with the old one, like version 0.44. So to be careful to participant to hands-on and then to build some, you get some code from the other GitHubs. So please check out the version of the Qiskit. And then tomorrow I will deliver some talk about machine learning implemented in the condensed matter physics, especially to predict the phase transition from the classical icing model and also SSH model. Please, before we go further, please attention to the announcement in the Discord channel about preparation for the hands-on session about installation for today and tomorrow. Okay. Okay, I will share my screen. Okay, maybe I'll share first. Okay. Okay. So all the material hand-on session I will upload in this my GitHub. Please take carefully, and then if you have faced some the installation about the Qiskit and etc. like a machine learning package, you can use the Google Colabs as an alternative. So and maybe the first one is I give you some. Okay, hang on a second. Okay, I'll give you how to installation first, the how to maybe step into quantum computing using Qiskit. So the first one, if you using the Google Colabs, please follow the instruction from my GitHub account. Can you click these links? This code will be copied in your clipboard, and then paste in your Google Colabs account. So like this, if you installation as run successfully, you can find that your Qiskit and install in your system. Okay. So yeah, in other word, when you because I fancy enough using the Ubuntu and the Visual Studio Code, and then try to using on my Python environment. So the Python environment give you some flexibility to construct some the other libraries, not only in the Qiskit but also the machine learning to not to conflict between the each package in the Python. So in the my computer, I have installed in Python environment. So you have to install this or follow my instruction in my GitHub. So the first one, and you could try to create a virtual environment in your computer. Arbitrary US, you can use Linux and also the maybe Windows. But then if you Windows and also inside the Windows provide some the Ubuntu subsystem, so you can follow this instruction, and then you can jump into the environment like that. This one I have the many environment. So there's why this I doing this classify this environment, because the different environment have a different version of the module, like the NumPy and SkyPy, and also the etc. like Matplotlib and so on. So to avoid this conflict, I try to access my my virtual environment on Python. Yes, sorry, it's Qiskit. Conda activate set. So yeah, this one is I jump into the Python environment. So I try to access my my file. Okay, so hang on a second. Okay, this one I try to. Okay, sorry, hang on a second. Yes. Okay, so if you have installed the Virtual Studio in your laptop, you can type the code dot. But if you don't, you can use the access to Jupyter Labs. So this one very convention. Okay. 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 In the quantum circuit, so because I have installed the newest of the Qiskit in my local laptop, how to check with my version, you can try to like this board. So import the Qiskit. Our version is installation in your local computer. This is a very very crucial. You have to see how the version of Qiskit you install your local computer, because the different version of the Qiskit have affect the code you have compiled, because especially when you have maybe the professor have the student, and then maybe in the long ago when you're using the Qiskit version old version like the lower than 0.44. So this Qiskit not going not compile very well in the version Qiskit in version 1, because the very different setup and different syntax. Okay. Okay. So it's my computer. I've installed the version Qiskit and version 1. So how to construct a quantum circuit in my local PC. You can from this declare like from Qiskit import quantum circuit. And today I try to create some quantum circuit to provide to qubit, and the qubit 1 I apply the Hadamard gates, and the qubit 1 and 2 apply the CNOT gate. Please take carefully that in Python indexing initially start from the 0, not 1. Like a MATLAB is indexing from the 1, but in the Python especially indexing started from the 0. So please carefully, and then you can draw the circuits. So this one, the circuit Hadamard gates in the qubit 1 and CNOT gate in qubit 2 and 1. So if you not fancy enough about the MPL, the draw circuit, the very various to show your quantum circuit, you can use only this one. This will give you binary. Okay, so binary quantum circuit, and then maybe you want to provide some publication on your scientific paper. You can use LaTeX and give you some. Oh, sorry. You can like LaTeX if you install like the LaTeX package, but in my lab computer that doesn't install my LaTeX. Okay, so I back to MPL. So okay, this one. If you have done with the first one is as the method, actually you jump into the quantum circuit. Okay, the next level is how we are dealing with the time evolution circuit. What does that meaning? The time evolution circuit, when we are dealing with some quantum state involving in time. So like involving like various time and times a different quantum state. Okay, so this one you can in the newest circuit Qiskit. Okay, the circuit as Qiskit provide some the various module like you can use the Pauli evolution kit to find some exponential unitary exponential matrices, and then using the sparse Pauli metric to doing some operation in a Pauli matrices like this one. Okay, ZC1, ZC1. Okay, so okay, we try to find some the quantum circuit in 3 qubits, and the qubit 2 we are to find Hadamard gates, and then we try to add some arbitrary quantum state, but dealing with the involving in time, like exponential matrices. So we are to find, like some before, the sparse polymetric ZC1. ZC1, this means that, okay, hang on a second. So okay, ZZ1, that's mean that you are doing operation a polymatrices Z, like you've not familiar with this, with Kronecker product with Z, and then Kronecker product with the identity matrix. Okay, so this means like sparse polymetric, you can check the to find. So okay, so we'll try to find the exponential matrices, and then
Isul?
yes.
Yeah, can you share your file to the participant? Maybe
Okay.
chat box or Discord.
Okay. Maybe after this hand-on session, I'll upload my file into my GitHub. So
I think you can share your file so the participant can follow your slide. Maybe,
okay.
Okay, thank you.
Okay, so what a second. Oh, okay. Hang on. Okay, so here we go. Okay. Okay. So please, everyone, you can install and follow my rules. Okay. I continue again. So okay, you try to find some the find the exponential matrices in your quantum circuit, and then try to compose, like this mean compose, like the add between different quantum circuit, and then we can use it that, like before the compose, that's mean that you add some different setup of the quantum circuit. It's fit in one the circuit to define it. So like this one is exponential IT. That's to define some the unitary time evolution, and then okay, how to deal with the different setup or different quantum circuit like this. So maybe you have an idea. Okay, I try to find some arbitrary quantum circuit with the have a number of 4 qubits, and then the second ones I have some idea. Okay, I have a different setup, a quantum circuits with 2 qubits. So how to combine with the different circuit in the circuit A with the circuit B, but it should be noted that have a different qubit. And the circuit A have a qubit 4, but in circuit B have a qubit 2. So how to combine this different setup of the quantum circuit? You can employ this method. You can circle A compose circle B. This means though, okay, apa? Yes, at the different setup, and but in the circle B, I want to put in the get Y and get Z into the qubit 1 and qubit 4. So how it's this images, you can see that Hadamard gets as keep in the qubit 1, but qubit 2 defined by Y. Okay, by in the circuit A, and the qubit 4 define the qubit Z as Z gates. Okay. Okay. What about when you have a circuit organized? This is maybe okay. Maybe the some okay, you have the blanks how to define some quantum circuit. Okay, like before. Okay, maybe these ones. Okay, I try to I have defined Hadamard gates in the qubit one, but I don't know how to continue the some gates after the Hadamard gates. So you can define some arbitrary gates as follow this like before this initial instruction with the qubit one, a qubit 2 and through the qubit 4. So we can define some the arbitrary circuit, but not especially specifically define some gate like Y gate, X gate, Hadamard gate, and a CNOT gate. Okay, and also we could define some control gates, but not define specifically. Okay, like this. Okay, this is very interesting in the Qiskit version 1 because I have a two different setup. Okay, I don't know how to get in the circle P, and I don't know get in the CNOT gate. Sorry, control gate in here. Okay, so in the Qiskit, we could decompose from the arbitrary some maybe infrastructure of the quantum circuit you have defined like this. You can decompose of the circuit A from this one into this one. Okay, this one is represented by the we get some the quantum circuit from the arbitrary definition you have. Maybe you have you don't have idea how to define some circuit, but in the Qiskit, maybe check the this user how to define this one. Okay, try to fractional quantum. I can solve for the packet cascade. Try to match some circuit that make the circuit have the unitary Hamiltonian. Okay. So, what about a parameterized circuit? So, in the parameterized circuit, like we define some arbitrary variable like angle, theta, pi, lambda, and etc. So this one is because to optimization large circuit, where we are dealing with some gate imply some maybe some angle. So we could define with the parameter this one is with angle, and try to define angle into Rx gates in this one gate. So after that, we try to transpile that's mean in the Qiskit version 1 is like a translate into the optimization in the Qiskit. So we have to translate in the circuit Rx into try to match or U kits or CX kits. And then we could also change the parameter theta with some arbitrary value, like from the 0 up to the 50. Okay. So, okay, I continue. In the previous previous explanation, we are dealing with the how to build some quantum circuit, how to define quantum circuit with the arbitrary. You don't have idea how to define some quantum circuit, but you have maybe infrastructure. Okay, I put this one Hadamard gate, I put this one maybe X gate, but the other ones I don't know how to continue. So, and then we can parameterize some variable quantum circuit. So the next one is how to analyze a quantum circuit, like compute the state vector, and also we can compute the probability and also unitary operator from the quantum circuit. Okay, so try to maybe the first one we try to define some another quantum circuit like Hadamard gates, defined in qubit 1, in qubit 2. We try to compute state vector of the system. Okay, it should be noted that in a cascade, the initial state of the system may be this one. Okay, so I try to, okay, this one is okay. Oh, sorry. Okay, maybe I can. Oh, sorry. Okay, okay. In this one, I define some initial psi, and this one is final psi. Okay, so okay, initial psi in the cascade initially start with the zero state. Zero state, this means that spin up. Okay, so the state vector in here, this means that you compute the final state represented by psi f to operate from the some operator. We can define the state vector, the state of final. But if you want to change, this one is represented by spin up. If you wanna change, okay, I want to initially from the spin down, you can maybe employ some escapes before the Hadamard gates like this. Okay, maybe the key would 0. Okay, maybe from scratch. Okay, you can escape, define the escape first, and then after that is Hadamard gates. Okay. If you want this spin down, this is spin down. Okay, that's key ones. Okay, you are operate the X gate first and then Hadamard gates. Okay. 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 So I've continue again. So we try to compute the state vector of the system. We are followed this state vector of the system operate with the Hadamard gates. But if you want to display this fancy enough using LaTeX, you can use it. Okay, this one. Okay, this one that state vector of the system represented by the 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then what about the state vector of the system? Okay, we can draw it with a plus pair that the system and qubit 1 represent the state vector going to the x direction and also in the qubit 2. Okay. Oh, what about how to compute unitary matrices? What does meaning unitary matrices? Unitary matrix here to compute this. Okay, to compute this gates. So you can maybe these circuits you are doing with from the scratch. Maybe the write down. You can you find the unitary matrices with the Hadamard gates, Kronecker product with the Hadamard gates. Okay, so yeah, this one is represented by unitary matrices of the system. Okay, but we're dealing with the some number of qubit up to the maybe 24. Maybe I give you later how to dealing with the large qubit. So you can define this Q operator circuitry. You can find that this one is matrix unitary matrix from the circuitry, and then how to compute probability of the measuring state of the circuitry. We have found that 1/4. Okay, 0.24. Okay, this probability of the find the system state in the measuring state. What about how to compute density matrix? This maybe you are dealing with the quantum info with the density matrices in the cascade provides some compute the density matrix. We try to compute density matrices, and then to maybe visualize the density matrices in the circuitry. This one you can see that there is no value in the imaginary row. Yes, you can see that there's no imaginary row. So only in the real part of the density matrices. Okay, and then how to compute the partial trace and the system try to in the subsystem and 0 or the index 1. So from the and trace from the partial trace in the row AB. So we can fold that this is 4 times 4, but we are compute the partial trace in the 1 indexes, subsystem 1. Like we have the row AB, we try to the partial trace respect with the P system, P subsystem. We can find that row in the subsystem A. Okay. And then how to dealing with how compute the expectation value of a sub-variable. And then we can doing this circle tree. This is from the state vector and then expectation with the unitary circle. You follow that expectation value of the circle tree with the follow like before. You can see this one. Okay. And then how to we are dealing with the how to sample count when we try to maybe have the sampling, every sampling have a different account, like a probability of the system put in the some specific state, and then try to we are sampling with 1.1024. We obtain that the probability of the system in the state 0, 0 represented by 255 and etc. And then we could visualize this count between using a plot histogram to represent by count. But if you not convenient about it, you can use the plot distribution, like mean that you're dealing with the quasi probability of the system. Okay. So this result have fit enough with the match enough with the theoretical. Maybe we can jump into this one. Okay, it's a 1.25. You can check this quasi probability of system with the sampling this system. Okay, you can try to large enough, and when you sampling large enough, the error of the sampling between the sampling and the ideal system close enough. Okay. And then, okay, how to synthesize unitary operation? This one is very intriguing for me. Okay, so in the case this version, maybe, and you have, I don't know how to define some the quantum circuit. I don't know, but I have some unitary matrices. Okay, you have some unitary matrices, arbitrary unitary matrices. How to translate the unitary matrices from the matrices, from the matrix into the quantum circuit. Okay, so we have defined some arbitrary unitary matrices like this. Okay, and then we try to translate from the this one, okay, unitary matrices into the quantum circuit with 2 qubits. Okay, and then try to mix up the unitary matrices with the quantum circuit. Okay. After the match between two variable, two quantities, and then we try to compute the matrices, but represented by the quantum circuit. Then we have tried to decompose the matrix, and we obtain that okay, these matrices have the I think it's close enough with the arbitrary unitary matrices you have defined. Okay, how to prove it that your recent size quantum circuit with the unitary matrices you have defined? You can check again. You can check the data and then to compare with the previous one. You can see that okay, so all of quantity of the system have the match all of it. So this means that okay, we can conclude that the quantum circuit from them translate into the matrices have give you some fit enough with the unitary matrices you have defined, some arbitrary. Okay, but it should be noted that this method is not maybe not sufficient enough, because when we are dealing with the maybe jump into the real system of the quantum circuit, like when you have access into IBM quantum computing, so this method cannot sufficient anymore. So we could doing the Kiskin transpil. This means that your quantum circuit translate into the topology based from the quantum circuit in the IBM, okay, to high optimization level. So this one is from the optimization. Okay, so what about when we try to what about when you define some unitary matrices into the Pauli basis? So you could sum this, and then from Jupiter U, that's this one give you some some combination of the operation of Pauli matrices to provide value same with the arbitrary unitary matrix you have defined. Like this. This one is operation of the system, but you have to emphasize that this means like you maybe linear combination, like maybe I this mean I Kronecker product I, and then this one no coefficient. So this is coefficient 1. So 0, 24, I, sorry, my writing is so bad. So it's Kronecker product I, and then try to define some, the second one, the plus 0, 25, operation I, Kronecker products with the X, okay, and so on and so on. This is combination, linear combination of the system. Okay, if you can from scratch from this. Okay, so what about we are dealing the combination of operator? There are so many combination of operator. We are dealing with tensor product, textural expansion, and then we are the composition and also the linear combination of the operator. We try to find some the operator in the X Pauli matrices, and also Z. A tensor B, that's mean you can define the A Kronecker product B. Let's follow as this row, this one, and then but you want to maybe you are the like the simply enough, you can follow this one. Okay, this is same way, but simply enough. Okay, And then the tensor expansion, this is different with the A tensor P. A tensor P A cross Kronecker product B, but in the tensor expansion, A expand B. This means that expression P Kronecker product with A. That's a change of the subsystem. Okay, you can use the simply enough the method. Okay, what about the compose? Compose that means the multiply matrix between A and B. But in the cascade, if you doing A dot P, you have to find from true. So A cross B, that's mean that we are dealing a multiply matrix between B and A. But in the A compose B from true, it's equal mean that A dot B. Okay, so please please carefully how to define some composition of the matrices in the operator. What about linear combination? Linear combination of the operator, we can addition, subtraction, and also scalar multiplication by complex number. So this one you can define this one, this method, this way, and the simply one you can follow this one. I have explained it before. This means like plus as minus enough regarding from the coefficient. Okay. And then how to check that OPS, this one, F a unitary. This is simply one. You could check the your unitary operator have unitary or not. You can check this unitary. This means that you have the maybe arbitrary case, this taker, and also we have operational heads equal identity operator. Okay. Okay. So, okay. Okay, maybe in the previous one we have dealing with how to operation with the operator, and then maybe we are to the okay maybe we are to face the some hard challenging to quantum circuit. What about when we are dealing with the simulated circuit using air simulator and also fake provider? Fake provider, this mean that if you have no access in the real system quantum circuit, maybe an IBM, so the IBM provides some the package to mimicking the real quantum circuit, but you could doing compile in the local PC. So this means that fake provider. So fake provider that's mimicking the topology of superconducting qubit, like when like the how many qubit if you want the access, like the 10, and then up to now we can access up to the 5027 qubits, but into the real system. But the fake provider, you can choose every top one to topology you represent it. Okay. Okay. So to maybe we are dealing with the similar circuit with the air simulator and also fake provider. I to find some the key HZ state. This one try to we can define the key HZ state with the arbitrary number of a qubit. So and then how to compute some the count of the simulation of the system with the error package, and then it's like this, and then you can circuit, you can insert them circuit quantum circuit you have defined, and also sampling how many sampling you want to define, like maybe 1000 and also 1024, and you have a high grade enough that weight like to H194. Okay, the method this mean that you could define some the method to simulate of the quantum circuit, but I have explained later. Okay, so we are define the setting of backhand of the air simulator, like sim air simulator, and also we are doing to transpil. Transpil, that's mean that translate from the quantum circuit you have defined with the topology in the air simulator. This one have secret and a sim air, and then we can execute the circuit with the sim air run with your transpil, and then how many sampling to define have a shot, how many you have repeated some measurement, and then how methodology you define and got some result, and then with the last week could compute the account of the how many count have occur in the many sampling. Okay, maybe the first one in which we try to define a QHZ state with the 3 qubits, and then this is you can see how the quantum circuit and QHZ in 3 qubits, and then we try to simulate the QHZ state using air simulator, and then we try to sampling with this one. You can change what is difference you have result. Okay. Okay, you simulate the air, and then we could obtain that from theoretically, when we've count the measurement only give you 2 state and 1 state and 0 state. This is close enough. What when to plot the histogram of the count and also the quasi probability. It should be noted that the QHZ state distribution from anything that give you, in the ideal case, it will give you 1/2 probability. Okay, 1/2 probability and a 0 state and 1 state. Okay, and then what about when we are dealing with the large qubit? We are dealing, maybe sorry. Okay, I have mentioned in previous one. We try to tell the circuit about with the QHZ state in the 24 qubit. We are dealing just the phase of the qubit. Okay, this one. Okay, it's very hard to doing the from scratch to operation of the circuit to doing a unitary, and then how to dealing with the large qubit. In the air simulator, provide some the method like matrix product state. This method represented by the network quantum network. So we try to combine some methodology from matrix product state to define that we have the feeling that we have found that same as before in the we have defined in 3 qubit in QHZ. There's a 0 state and only the 1 state. Okay. Okay. So what about when we try to plot the histogram? Okay, the histogram with the count, it's like this same enough with the ideal case. And what about when we are dealing with the noises? So in the real system of the quantum computing, your simulation on your measurement give some error. So when we are dealing measurement, okay, this theoretical QAOA state is only so many qubit we have defined. It's only give you 2 output, like a 0 state and 1 state. But if you try to dealing with the real system, the measurement of not give you some two output of the measurement like a 0 state and 1 state, but differs from the other state. Okay, so this one we try to mimicking from the noises into the real quantum system at IBM, but today we are dealing with the try to only to find the depolarization error. So we try to depolarization error with the probability only 0.1, and then with the probability depolarization error to put into the QP2, and then we add some error only in CNOT gate. What about when not in the CNOT gate? Okay, you can define as arbitrary error, like maybe you can UKits and etc. etc. Okay, so we are following this result, and then we are compare with the ideal KIZ in 3 qubit with the ideal in noises. Okay, you can see that the in the ideal case, of only represented by the blue colors, only give you to output of measurement, so 0 state and 1 state. But if you introduce the noises with the depolarization rates, depolarization error, this measurement not only in the 0 state and 1 state, but differs into the other states, like 001, 101, and so on, so on. Okay. And then, okay, so, okay, maybe we try to, maybe the participant, I don't know how to find some error like the from effect from the depolarization error and also temperature from the superconducting qubits. So we can use the fact provider. So the fact provider I have mentioned before that fact provider that's mimicking the behavior of the IBM quantum system with the snapshot of the topological of the superconducting qubit to find into the coupling maps, and then basis gate and also qubit purpose like the depolarization error, temperature error, and error rates, and etc. etc. If maybe maybe this occur when we are dealing the real system, you can. And this one is how to dealing with the fake provider. But if you more detail how to fake provider have provide in the cascade, so you can click this one and maybe to jump into the real links. So this one you can study it, how to access a fake provider. So fake provider give you maybe some preliminary result before when you have some access in the real quantum system. Maybe have a preliminary result, and then there are so many fake provider like fake Bogota, Brisbane, Brooklyn, Cairo, and all, and so on, Geneva. What does the meaning of this one? If you click this one, maybe I try to click a fake Jakarta. So it is. I said the Jakarta only give you some backend with the topological quantum circuit with the 7 qubit. Okay. What about when we are dealing with I want to my system have the large enough, maybe it's with 50 qubits. So you can look for some another fake, maybe a fake Manhattan, and also maybe Mumbai. Oh no, okay. Maybe Hanoi. Oh no. Yes, you can check first one by one to sufficient with your system. Okay. I go back to into this one. Okay, try to I compile this one. There's definition function how to compute the fake provider from the cascade, and then in this tutorial, I will give you some fake provider from the fake Jakarta. We are dealing with the 7-qubit topology quantum circuit. You can change anything. You can change whatever you want, but from the maybe the Argentina, you can from Santiago, and then maybe Prague and Perth, Paris, and etc. and Mumbai. Okay, so after this one, okay, so I have this because we are dealing with the transpil. That's mean transpil. I have mentioned before the transpilation process. I have rewritings. Transpilation process, the rewriting the given quantum circuit, your system, but you are defined in the local computer to match topological specific of quantum devices to optimize the quantum circuit for executing a noisy quantum system. You don't have to confuse that when you use some another fake backend, like maybe this one is fake Jakarta, and then you are changing with the maybe fake Cairo, Mumbai, and Tokyo. You maybe some transpil have a different circuit because have a different topological quantum circuit. Sorry, topological superconducting qubit. So it should be noted that you have to find some difference of IPM runtime. You have a dealing with a difference topology from the transpilation of your circuit. Okay, I will give maybe I will give you some example. We are dealing with the QAOA state. Okay, you don't know that QAOA state that's like have quantum circuit like this. Okay, sorry, maybe jump into okay, maybe this one. Okay. Try to dealing. Okay, in your circuits, a QAOA is in 3-qubit like this. Okay, but where transpil into with using topology in the fake Jakarta, it's not the same with your quantum circuit you have defined. Okay, this one transpilation. Okay, this one. You can see that a difference configuration of the quantum circuit between your input with transpilation after translation from the topology quantum circuit. Okay. What about we are changed with the not in fake Jakarta? Maybe I try to. Okay. Oops. Okay, we are dealing with the fake epoxy. Okay. Maybe. Guess once. Okay. Backhand 2. Okay. So we are changing with the backhand 2. This one is the same. Okay. Maybe try to. Okay. We're change with the backhand 2. Okay. Please try to looking this circuit. We are try to define another transpil backhand. We are dealing with that. Sorry. Okay. So I found. Okay, this one. Okay, you can see that. So if you define some another backhand like with the fake Jakarta chain with the fake epoxy version 2, this transpilation give a different different quantum circuit, because your input try to maybe in the topology of your system try to optimize the quantum circuit match with the topology of the quantum circuit, the real quantum circuit. But in this tutorial it's mimicking. Okay. I give you some maybe enough. Try to okay. So okay, we are dealing with the fake Jakarta. Okay, so okay, so let's try this. Oh, hang on a second. Okay, oops. Okay, real. Okay, so maybe I jump the first. Okay. Okay, so wait a second. Okay. Back to the okay. Oh, sorry. Okay. Okay. So, what about when to? What about when we try to represent by the count between from the fake providers? So we have the dealing with the real system. Give you not the ideal system in a 0, 0 state and 1, 1 state. I have mentioned before, but it's spread into the another maybe another another state, like as 1, 1, 0 and 0, 0, 1 and 0, 1, 0. Okay. What about when we are try to maybe this compare with the ideal state, a noise state, and also a fake provider with the represented by a fake Jakarta, and then you can see that fake Jakarta have a large enough give the near with the ideal state, but in the compress with the, maybe in the different state have compressed with the error, like, because in topology have different setup have maybe give you a different error. So in the meantime that the scientists also, because your measurement from the real system give you some the error. So sometimes that in the scientists try to push the error with the like the error correction. Okay, so we are dealing with some the basics to find the quantum circuit, how to analyze the quantum circuit, to define a unitary matrices, state vector, density matrices, and also we have the dealing with how to error simulator, and then noise, and then fake provider. We try to, how about we jump into the real system? In this tutorial, I'll give you some bonus how to simulate a quantum many-body dynamic. So I try to reproduce from the paper from the Adam Smith. So this Adam Smith tried to translate the some system like the quantum Ising model with a 1/2 chance, and then in the system have a different spin configuration in as initial state, like the domain wall configuration. This means that we are dealing with the initially from the zero spin down, spin down, spin down, and then spin up. but also dealing with the nil state like spin up, spin down, spin up, spin down, spin up, spin down. Okay, so this one's Hamiltonian of the quantumizing model, but in this paper, I try to dealing with this only the X exchange. So we are defined by U with a 0, and then H a 0 is only this X exchange. Okay. How to translate quantumizing chain in the quantum circuit? So maybe the clever method have introduced by the Adam Smith. He tried to using the schematic implementation of trotterization evolution. Maybe you have the you obtain some explanation from the Professor Adrian. So the trotter evolution, we try to some exponential matrices you can split by 1 by 1, represented by the trotter decomposition, and then in this tutorial we are dealing with the C. We try to symmetric trotter decomposition. In the AZ, this block AZ, this means that initial state you have defined, like you dealing with the domain wall configuration and also nil state, and then PZ that represented by this one. Okay, how to dealing with this, and then C dealing with this. Okay, so how to translate from this configuration symmetric trotter decomposition into the quantum circuit. So this one, there's anything else about the decomposition of the translated quantum circuit, the only 3 gates you can construct. The only configuration from the RxJ, Rx gates, Ry gates, and also Rz gates. The config and C node. So the four gates, we combination of the 4 gates, we could define some the matrices, anything. Okay, so this means like introduced by the optimal decomposition for NAP gamma is given by what theta is equal this one, and pi is this one, like this one. Okay, we are dealing okay, the first one is how to define this. Okay, we try to define a block. A block, this mean only the initial state, because I have defined when we are dealing with the initial state, we are spin down first. Maybe it's maybe number of qubit, and then we are after the first half of the qubit, we are split flip spin, we spin up, and the nil state we gonna spin up, spin down, spin up, spin down. But when you are maybe you change with the not provided in my 2 codes, but you face that invalid initial state because I've not defined yet. And then this one, how to define block P blocks and also C blocks. Okay. Okay, how to compute the trotterization of the circuit, because trotterization of the circuit combines from the A, B, C, B, or the configuration after A, after P block and C block, and back to P blocks. This one, you can see that A blocks initial first, attack to superior. This means that I want to block A blocks doing the first calculation, and then P block calculation, C block, and P block. And then we are dealing with the number of qubit 6, and then delta T is represented by the jump into the trotterization step, and the number of thread I only define 1. Why do I defines only one to give you some representation of this quantum circuit. Okay. And then I have initial state with the domain wall. You can change with nil state. How about the quantum circuit? Okay. Oh, sorry. Oh, sorry. I have not compiled this one. Okay. 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 This one. Okay. So this one is mimicking from the quantum circuit represented by the XX spin. This one, because we are dealing with domain wall, if you're dealing with these ones, what about nil? I have mentioned before that initial state from the cascade it start from the spin up, okay? But if you want to concentrate with the spin down, you can employ the X gate first until in the barrier. This one is represented by the P gates, P block, and then we define some the C block, and then define some P block again. Okay, so this one is P, C, and P. Okay, this systematic Trotter decomposition. This is A. Okay. And then, what about we are dealing with some, not only the number of totalization only one, but maybe check until 24, 25, and this one. Okay. What does meaning of the definition? I have this summoned before this, how to simultaneously error to define some the account of the measurement, and also I try to we are dealing with the mimicking the real system with through the fact provider, and also how to define, how to compute the sigma z expectation. So in the Adams Smith paper, we are dealing with the local magnetization with sigma z in I. This means the local magnetization in the maybe in the first in the system. I try to define with the dealing with the in the qubit 4. So okay, how to compute then, because we are dealing with the 6 qubit. Maybe you can cut some difference 6 sorry 1 2 okay 6 combination of the 6 qubit, but we are focused on in the qubit 4. Okay, maybe 1 0 0 0 0 1. Okay, and etc etc up to 0 1 1 1 1 1 1 1. Okay, it's 1. Okay, we only focus on this this qubit. So this represented by the local magnetization. Okay. Okay, and then okay, after that Trotter evolution, because this system try to each Trotter step, I got some the count and extract some information, and then collects the some information to doing expectation value of the sigma z expectation. Okay. Okay. And then we try to okay. This one I try to define backend effect Jakarta with the sampling with the 1 0 to 4, and then I trying to calculate the expectation value of ideal case and mimicking. Oh, sorry. Okay, so maybe I. Okay, so Sorry, maybe try to. Okay, so I want to compile all of it. Okay, hang on a second. So okay, this one. Okay, this one is the result of the probability of the system from the quantum Ising chain in the XX model with the compare with the third recession, maybe the ideal case, and we compare with the maybe IBM. So we have defined like this. This one's this one that with maybe starting from the probability that spin up in the zero state. Okay, so maybe it should be noted that in the domain wall and domain wall, we try to split into the half between spin down, spin down, spin up, spin up. Okay, so we are dealing with the number of qubit is 6 qubit. So we are face the domain wall. This means that okay, we are given a spin up, spin down, spin down. Okay, in the first half, and then the second half, and spin up, spin up, spin up. Okay, so because we are focusing on the qubit 4. Okay, it's been noted that qubit 4 initially in the state as in the initial state in the time equal to 0, initially from the 1. Okay, so sorry, the spin up, so represented by the 1. Okay, I think okay, this is maybe this is clarified. And then after the time, evolution of time, the configuration of the spin have to maybe have a different configuration of the spin, maybe spin, maybe flow to flipping like this, and then okay, try to combine the current state after a few seconds. Try to spin down. Okay, but and if you using IPM Fake Jakarta, because yes, because Fake Jakarta have the configuration only the 7 qubit, but you can use a different setup. I have sorry, I have provide some this one. You can use fake POC. Why I use the fake POC. This try to reproduce Adam Smith, because Adam Smith use fake POC, but not using fake provider, but the real quantum IBM. Okay. Maybe from the participants, you can take note that you can try to difference configuration, not only domain wall. Try to with the nil states. What happened with your calculation, and then try to higher number of qubit, not only 6. Try to 8, 10, and then what about how long throttle steps? Not only 25. Try to maybe 100. So what happened with your system? And then sampling, try to not only 1024, but try with the in the paper is you can use 8192 in the Adams paper. This is statistically can reduce the different result from the ideal case with the error. Okay. And then maybe you can change with because we are focusing on the 4 qubit represented by the local magnetization, try to with the maybe 6, the 6, you can try to 6. Okay. So maybe I think it's enough for me. If you have any question, please raise hand. But if you maybe if you're shy, if don't understand with my hand-on session, you can ask me from the Discord channel in the hands-on session day ones. Okay. Okay. So okay. So maybe try to read some the okay. Maybe I try to okay, from the Dr. Fauzi Rahal. So what specific algorithm or method are used to simulate quantum many body dynamics and digital quantum? Specific algorithm is this is okay. We are trying to the best one how to fit the quantum circuit extract from the unitary operator. So because we are define some the directly to define some the Hamiltonian, especially in XXY model, we are facing of difficulty how to extract, how to define some quantum circuit. Okay, so the quantum circuit, the first one is we are trying to split the exponential matrices, become the piece by piece. Okay, represented by the Trotter decomposition, and then from the decomposition, we are try to match with the maybe I have a send if you show you the optimal decomposition for n. So this one is the anything's unitary matrices could represent by the optimal decomposition. Yes, okay. Only this Rxz, Ryz, and so C naught gates. So this one is how to. But if you okay, maybe the challenging is because okay, maybe like we are to match enough to try to close in. Maybe the we try to match some the unitary matrices to quantum circuit. Difference between the quantum circuits with the system maybe the immerse some the error. That's the difference between the configuration between the real system with the mimicking of the quantum circuit give some error. So some error we are I think we can run away from the error because we are not maybe the mimicking of the quantum circuit not the same with the unitary matrices. Okay. Okay, maybe try to. Oh, sorry. Okay, so okay, maybe when I. Okay, so sorry. From the Dr. Manrugan, I think what is rule of ancillary qubit is represented as quantum machinery simulator. Okay, as far as I know, but in this tutorial, I not mention ancillary qubit. So ancillary qubit means from that we are dealing with a fractional quantum eigensolver. But in this tutorial, I'm not deliver about it, but we are okay from the scratch how to dealing with the when we are using quantum icing model, so to define this system. Okay, maybe if you not you can ask me in the quantum Discord. Okay, so okay, from A2 and Ocon, can this quantum circuit be simulated using quantum espresso package? And today, I will say that no. Yes, Dr. Edwiasde, I give you no. But if you are maybe if you are dealing with the quantum circuit with the quantum chemistry, you can use packets from the Pennyland. Okay, from the Pennyland, you could define some the calculation to define some the ground state energy and also the potential energy surface of the system. But but this tutorial not give you. Okay. So okay. Okay. Question from the of Fauzir Halken. Can you provide more detail on the quantum circuit and gate operation used in the simulation? Okay. So I have mentioned that to construct of the quantum Ising chain model is you only this is interesting method. You can only not maybe the some other gates in the cascade like U gates, SU2 gates and SU and anything else, but is anything else some quantum circuit you could construct only from the I have mentioned 4 qubit, 4 gates like RY gates, RX gates, RY gates, RZ gates, and then C0 gates. Only 4. Okay. So yes, can we slowly? Yes, as in the cascade available to download. Yes, of course, you can download it, but from the terminal. I have give you maybe you miss my explanation, and then you can use only this install the package Python with pipe install cascade from the anything else but the cascade, and also cascade IPM runtime, cascade visualization to visualize some plus pair and density metric and cascade error to find some simulation. Okay. So, there are any question again? Okay. Okay, I think it's enough. Okay. Okay. So, yes, because I am the last of the hand-on session in today, so it's already 3 p.m. at the Central Europe time. We are sorry that we are the end of this second day of the workshop. We will continue this workshop tomorrow, and the final day of workshop. Please come again from the 10 a.m. Central European time, and hopefully you enjoy the workshop. Thank you very much for your enthusiasm and passion. We will end the Zoom meeting soon. Bye-bye.